Hi, my name is Charlie Zeiss. I am the owner of Stargate Pyramids and also the chairman of the Pyramid Science Foundation. And in that latter capacity, I've been studying what it is that makes pyramids energetic for the last 8 years. And I have come to realize that the golden ratio seems to be at the heart of the energy generating capabilities of pyramids. As I've been doing that, I have also been studying other areas in our universe where these very same geometric angles show up. And some of those places include castles, ancient architecture, our Gothic cathedral steeples, and also other areas that you wouldn't necessarily think would have these angles, such as the field of fluid dynamics. So I've been studying those for the last 6 to 7 years, and had come up with a very, very profound amount of information demonstrating that a process that I now call golden ratio scaling was involved and was available to see in all of these different categories. The one area that I had not looked at, however, was nature itself. And I have to be honest at the beginning, even though I knew that these angles were significant in maximizing, for example, or minimizing drag in fluid dynamics. I figured that these angles had something to do with the ether, but I wasn't sure how that was actually working out. But I was also a little concerned about starting an analysis of nature because I, like most of you in the audience, at the time was still stuck in what's called local reality type thinking. And we'll get into that. But basically, what I have figured out is that there is a master algorithm at work in the universe. And that's what this document is going to be about. Because if I can, and I will demonstrate to you the existence of this algorithm in so many different places, you will not be able to walk away from this documentary without understanding that we have to be living in a simulation. So, what exactly is simulation theory? For those of you who are unfamiliar with the concept, you saw the movie Truman's World referenced a few minutes ago. Another example would be The Matrix, the famous movie, cult movie that talked about people living in a simulation and how they were able to escape. But what is simulation theory? Well, simulation theory is a hypothesis that suggests that we perceive as the real world is actually a simulated reality, often described as an ultra high-tech computer simulation. This theory posits that humans are constructs within this simulation, and it has been discussed by philosophers like Nick Bostrom, who proposed the original simulation argument. It suggests that if advanced civilizations can create simulations, they might generate so many of them that a randomly chosen conscious entity would likely be a simulation. Now, different people have different opinions about this, but Elon Musk, for example, thinks it's highly likely that we live in a simulation. Other philosophers and scientists in this area think that that number is much, or percentage is much, much smaller. After seeing this, I think you're going to be agreeing more with Elon Musk than perhaps with the others, because we're going to see this pervasive algorithm everywhere. And it's very, very challenging once you see it to not see that this has to be a computer simulation. So, what is the existing evidence of simulation? We have pixelation and quantization of reality. Now, what that means is quantum mechanics has revealed that certain aspects, such as time itself, is quantized. Space is quantized, matter is quantized, and energy. So, what I'm going to be showing is that certain processes within the universe are also quantized, such as growth of all plants and animals on our planet. Particle behavior. Elementary particles, such as electrons, exhibit properties only when measured, implying they lack definite status until rendered by observation. This is essentially the double slit experiment that we're all familiar with. Quantum entanglement, and this is key because the Nobel Prize was given for this to three scientists 3 years ago, Alain Aspect, John Clauser, and Anton Zeilinger. And they won the Nobel Prize in Physics in 2022, demonstrating how instantaneous influence of particles at a distance occurred. And this is called quantum entanglement. Another thing that demonstrates the existence of simulation is wave function collapse. Particles exist in probabilistic superpositions until observed, and this helps to conserve resources in a simulation. So this also is another factor that tends to point to simulation theory. Mathematical constants. We know that the universe is full of mathematical constants. There are fundamental forces such as gravity and electromagnetism that follow precise mathematical equations. And what we're going to find is that there's a simple mathematical equation that we can see visibly in the universe everywhere that controls growth. Speed of light limit. The speed of light as a universal maximum may reflect processing speed constraints in a simulation. It may be a way for the simulation itself to be able to project outward before we would actually be able to perceive it at a distance because of this limitation on the speed of light. Fine tuning. The universe's expansion rate, dark energy density, and matter distribution are improbably balanced for life. Certainly a topic that we're going to be discussing in future documentaries because there's some great research coming on those topics relating to what we're going to be doing today. And then finally, there's the existence of computer code that's been noticed in the universe already. Dr. James Gates, a theoretical physicist at the University of Maryland, has uncovered startling connections between the mathematics of supersymmetry and computer error correcting codes. Now, what's the visible evidence of simulation? Existing evidence does little to demonstrate those examples to demonstrate simulation in the visible world. And that leaves many of us, including myself, until I did this research over the last 9 months or so, that simulation theory, I thought of it as a purely kind of theoretical concept with no real practical relationship to our physical reality. But what I found is that my new research dramatically changes that perception because the research results that I put together are by far the most comprehensive set of visible evidence to date that we have that we live in a simulation. Now, how am I doing that? I have discovered a master golden ratio-based scaling algorithm at the heart of many of the organizing principles of the universe. Now, what are those examples? Well, here's a list of all of the things, and this isn't everything, but this is what I've done so far. We'll find these algorithms in the following places. All plant and animal growth on Earth. It's found in fundamental processes in nature, which we'll discuss. It's essential in minimizing drag in fluid dynamics applications. These angles are critical for maximizing the thrust of jet and rocket engines. These angles are found in all conical bore and percussion musical instruments. They're found in telecommunications equipment and technology. They're found in all of our human sensory receptors and our DNA. They're found in all major pyramid sites. They're found in purely aesthetic uses in nature. And you're going to be shocked when you see these because you would have never guessed that this was all computer simulated. We find this in ancient architecture around the world. We're going to find this in these angles in free energy technology. We're even going to find them in the angles between the stars in the constellations and in the street grids of major cities around the world. So that's quite an amazing set of features that one algorithm would be used for. Now, I'm just going to show you this. This is all part of an introduction, but these are essentially 18 angles which form the core of the algorithm that we're going to be discussing. But I just want you to see the angle names. B stands for base, and S stands for supplement. We'll talk about that later. But now I just want to show you the methodology and then examples from each of the major sections that we're going to be exploring in detail throughout this documentary. So what I did for each of those sections, I went to Wikipedia or other reputable sources that I could use to identify appropriate candidates. So, for example, if I wanted to look at all the leaves in the world, that's the first thing we're going to look at. I got a list from Wikipedia of every tree variety that was in their list, and I checked out their leaves. I did the same thing for whether it's flowers or musical instruments or rockets or missiles or whatever the thing was that I was doing. So I didn't do this with the intent of cherry picking. I didn't exclude anything from the research because it didn't match, because everything matched. Now, I obviously don't have enough space here or time to show you every one of these, but I have done an extremely thorough search and have used an extraordinary number of examples here to demonstrate that this is universal throughout the plant and animal kingdom. Again, here are the ratio, the algorithms, and the methodology. So to go through this quickly, these are the sections that we're going to be looking at. We're going to look at tree leaves. And you can see here, the two angles that are showing up are interestingly, the apex angle of the Giza pyramid, and that's why we call it G, because it's so essential in the creation process, but also its supplementary angle. Now, we'll be talking about this more, but this is a classic example of the use of supplements that cannot be explained except through a simulation. We're going to be looking at branching of trees and plants. We're going to look at the gross morphology of trees and plants. We're going to be looking at the root and tuber systems. We're going to be looking at leaf veins. These are just a gold mine of sacred geometric knowledge, the leaf veins, which I would have never expected, but just shows you how precise and how this algorithm is everywhere in our universe. It's going to show up in every flower petal of every flower on the planet. It's going to show up in vegetables and berries, fruits and nuts. It's going to take care of the angles in every single mollusk. 100% success rate in finding the angles in this algorithm within every mollusk that I was able to find. Aquatic animals, the same way. Insects, both their bodies and their antennas all have these, all horns and antlers of all, larger animals use these geometric angles. Butterflies and moths are just amazing examples of these angles as well. Getting into higher forms of animals, we're going to see that these angles show up in the faces of felines, canids and canines, birds everywhere as well. We're going to see it in mammals. We're going to see them in primates. We're going to see this in our human DNA. We're going to see this in our own physical anatomy as well. There's also the aesthetic uses that I talked about before. If you ever thought that the panda bear or the triangles on the tortoise were random accidents, you're going to find out that they are actually part of the algorithm and that all of these geometric angles are all the same, coming from the algorithm. Here's some other examples. We're going to see these are called chitons on the left side. Look at these angles showing up precisely on a small object. Has to be, cannot be anything other than an algorithm. Even the stripes on the zebras are controlled by golden ratio scaling. Now, moving away from the plant and animal kingdom, we're going to be showing after that these very same angles show up in the world of fluid dynamics. I've done extensive analysis of hydrodynamic and aerodynamic designs. We're going to be going through all types of equipment there. Musical instruments, you'll find this in drums. You're going to find it in the reed instrument mouthpieces, oboe, bassoon, clarinet. You're going to find this bore, these angles in the bore of all conical bore musical instruments, including saxophones. You're going to find this in all sorts of telecommunications equipment, free energy technologies, including ancient Tartarian free energy geometries. We're going to find it in the old star forts. People had not been able to do much with the geometries here. I have found a number of these angles, including the Giza and the Giza supplement angle in those buildings. We'll find them in the ancient castles, but most importantly, we're going to find these in the ancient pyramids. This algorithm, for the first time, has allowed every pyramid to be linked in some way geometrically, because the apex of each major pyramid site on the planet uses one of these scaling geometric angles. We're going to see this in the constellations. I have measured every angle in every constellation, and they all match up. We're going to show a couple examples in great detail, and we're also going to show some examples of this in the street grids in major cities around the world. Now, I want to give you a few viewing tips before we get started. This is going to be long, so I have included a timestamp so that you can go from section to section. I would ask that you watch the introductory section, the one right after this, before you go on, because that's going to give you all the background on how I came up with this, how I was able to derive it, what the angles mean, and the significance of golden ratio scaling. And then finally, you're going to want to watch, I've got anomalies and case studies spread out throughout the documentary. Some case studies that are just amazing examples of this in the plant and animal kingdom. So be on the lookout for those as well. Before we begin our introduction into golden ratio scaling, I wanted to tell you that I am not the first person to do this. Victor Schauberger, many other people have been rumored to have known about these geometries and used them. All of the people who used these geometric angles show up in all of the ancient or the 18th, 19th, 20th century free energy technologies. So we presume that they knew this, but this is the only piece of evidence that has not been, hidden from us that demonstrates that they knew this. So Schauberger invented a home power generator that ostensibly produced 10 times over unity, so it was essentially a free energy device using these very same principles. So before we begin to examine the results, I want to do some introductory topics. The first of which, for those of you who don't know, is what the golden ratio is. The golden ratio, or phi, is really a relationship between two or more objects. If you look at the little diagram in the middle of the page, you'll see that the relationships A plus B is to A as A is to B. Now, what that is defining is a relationship, a scaling relationship between two or more objects. Well, this isn't really an equation that can be solved per se, except by trial and error. But there are other ways of doing it, but just mathematically, that's about all you can do. But the golden ratio, or phi, is the only solution, making the golden ratio nature's natural scaling ratio. The golden ratio is not really a real number, but is a relationship, which we approximate as 1.608, and you see the rest of it there. Or phi is a shortcut name for it, and also the golden ratio. Now, what is golden ratio scaling? Uh, Nassim Haramein, that's his diagram on the left, and Dan Winters, his diagram on the right, have both demonstrated that the universe uses the golden ratio to scale all objects from the subatomic to the galactic. So we already knew that. And this research demonstrates that the universe uses a very precise methodology for organizing matter and information throughout the universe. Now, neither Nassim nor Dan, came up with a kind of a formula. That's what I have been able to accomplish here, is to figure that algorithm out. They did the basic work, but now I'm going to take it a next step and develop the algorithm, and therefore be able to show you visually the existence of this algorithm in nature. Now, we've known about golden ratio scaling for a long time. The picture on the left is one of many I could have picked, but it just demonstrates all of the golden ratio geometries that exist in the human body. You can find it in your fingers and the links of the bones in your arms, legs, and trunk and torso, and so forth. So it's clear, one-dimensional, we've known about for a long time, and we know that it's already cooked into uh, human beings and many other things as well. But I also wanted to show you that we've known about this, or at least certain people have. This is a Stradivarius a violin, and these are considered to be the best violins and violas in the, on the planet. Well, one of the reasons is because the Stradivarius violin strictly adhered to one-dimensional golden ratio scaling, and you can see that in the picture on the right-hand side. Now, we've also known of the existence of two-dimensional golden ratio scaling, and we can see examples of that here. The most popular one probably is the sunflower that's up in the top right-hand corner, but all of these have these geometric angles, and so we have even extended our at least conceptual knowledge of golden ratio scaling to two dimensions. Well, what I've done is to take it to third dimension, and that's where my work with Russian pyramids starts us on this journey. So how did I develop this information? Well, as I said, I was doing research into pyramids, and I make these pyramids with these very geometric angles that you can purchase from me. But before I could do that, I had to figure out what the angle was. Well, unfortunately, the Russian scientists who wanted to publish this research were prohibited from doing so, not by the Russians, but by the people in the West. They were prohibited from publishing by Western publications the research that was done on these. So I had to reverse engineer this. So I wanted to show you how this whole process started. And I knew I could figure the angles pretty well with a protractor app. And so I started to figure out various ways that I could come up with a geometry that would have the golden ratio in it that might match the geometry of the pyramids built in Russia. So what I did was I started by stacking. This is a two-dimensional diagram, but it could be in three as well, just as easily. I started with a circle in two dimensions with a diameter of 1, and I started stacking circles on top, each time dividing the previous diameter by the golden ratio itself. So in the first case, I had a diameter of 1, divided that by 1.618 and got 0.618, which is the diameter of A1B1. Then I do the same thing to get 382, 236, and so forth. Now, what's interesting is you could do that ad infinitum. You would never get to the top. But what you can do is now to construct the geometry in 2 dimensions of an equilateral triangle, and then very easily you can expand that out to 3 dimensions. It's beyond what we're doing here, but what I want to show you is that we have a slant angle, that's the angle at the bottom, of 76.345 degrees, and an apex angle of 27.309. Now, why is that important? Because once I saw that, I was able to immediately connect the geometry of the Russian pyramids, the current day Russian pyramids, with the ancient pyramids in Giza. So the Great Pyramid of Giza, as it turns out, I've done a diagram of these two on the left here. The smaller pyramid here is the Giza pyramid, and assuming a common base length of 2, I've then superimposed the Russian pyramid geometry on top of it so you can visually see what they look like. Now, what happens in this case is that all of these angles turn out to be, and distances lengths related to each other. If you look at the height of the Russian pyramid, 4.116, that actually equals 2 times the square root of phi cubed. The height of the Giza pyramid is the square root of phi, and the height ratio is 2 times phi. Now we look at the slant height, which is the 2 vertical sides of an equilateral triangle. Those slant heights are equal to 4.236 or phi cubed. The slant height of the Giza pyramid is phi itself, so the ratio is phi squared. But what's even more important is to see that the Giza pyramid has an apex angle equal exactly to the base angle of the Russian pyramid. So this is a major find, and gave me essentially the first two angles that came into my algorithm. Now, the next step, once I had those two, I decided to go, as I mentioned, look at cathedrals. I've looked at architecture, but for my purposes, the most important thing was to find these geometries in fluid dynamics. I measured every nose cone, every dirigible, every plane, every rocket, every missile. I've done them all. And what I found was, in addition to the G and the B2 angle, which is what those 27,309 and 76,345 represent in the algorithm, I found a B4 geometry and a B1 and a B.5. Now you might ask, well, how did you figure out what these were? Well, I had to do a lot of guesswork initially until I started to fill in the algorithm. And I have to admit, I made a mistake at first, because what I decided to do when I found the B4 angle, I thought that when I measured it, it was pretty close to either one of 2 potential solutions. I could either, with respect to the pyramid itself, and we'll get to it, I had a couple of different ways of figuring it, but what turned out to be right was all I had to do was to vary the base length by halves or doubles, and we'll get to that, to come up with these angles. So the very same angles that we found in the Russian pyramids, we're going to find in the rear of this cargo transport plane, and in the front and the rear of commercial airplanes. When we divide that again in half and have a base length of 1, we find the same geometry in SST nose cones. And then when we divide it again to 0.5, we find it in the nose cone of hypersonic vehicles. So pretty amazing stuff. And I got to tell you, I've been trying to get people in fluid dynamics to understand this for years. I now understand why they don't, because they had no context in which to believe this. So that's why we're going to be going over that as well. Now, before we get to the algorithm itself, I want to talk about anomalies. And we've got a number of anomalies that further prove the existence of this algorithm. The first one, and perhaps the most important single thing outside of the measurements themselves, was finding supplementary angles. What are supplementary angles? If you didn't take geometry, or if you've forgotten it like I had originally from high school, because that was a long time ago for me, supplementary angles are two angles that sum to 180 degrees. Now, there's no logical reason that I can see for that to happen unless there's a simulation. But adding those supplementary angles to the algorithm unlocked all of the missing links in numerous areas and subject matters that I couldn't have figured out otherwise, including, for example, the all of the pyramids. If I hadn't found the supplement, this was a major find, because many of the pyramids, particularly in South America, and the Pyramid of the Sun, the Bosnian pyramid, have one of these supplementary angles in their apex. So it's fascinating research. Oftentimes, you're going to find that supplementary angle associated with its other supplement in the same object, like a leaf. So it's fascinating. But when you see all this, you're going to say the pervasive use of supplementary angles can only be explained through a computer algorithm. All right, finally, we're at the angles in the base algorithm. We're going to go across column by column names first, and we'll come back and try to explain each of these. The first column is base length. So the base length, to go over to the diagram on the right, is measured or demonstrated here in the bottom. You can see the base length is just from one corner of one edge to the other. And that's what we're going to be varying in our base algorithm. And we're going to see if I've got two lines that are done in blue, the 5.236 and the B3. And let's leave those out for a moment so that we can just look at the rest. As you know, I told you that I had found the B4, the B2, the B1, and the B.5, and I had done that just by doubling or halving whatever unit I was working with at the time. I added to that, I expanded it a little bit to include B.25 and B.125. They're not necessary very much in nature, but when we get into other areas, we're going to find that they're important. So that's essentially the way the base lengths worked. I'll come back to the Giza and the B3 here in a minute. Let's talk about slant height. Slant height, again, let's go over to do our diagram. The slant height, again, for a two-dimensional triangle, would be the equivalent of this yellow line that's showing up in this three-dimensional pyramid. So the slant height is essentially the length of that yellow line in each case. Now, what's interesting is this variable stays constant throughout all of these algorithms. So our examples. So that's the one constant that we're going to have in each case. Now, the next column is called name. All I've done is to give each of these a name, and I'm just using the number and the fact that it's a base length as the name. So the base length with the length of 8 is B8. Now to get back to the Giza geometry for a moment. You'll notice that the Giza geometry and the B3 geometries don't really fit within the geometry and or the algorithm, as it doesn't seem to. But what we find is that if we were to look, let's look at B3 for a moment, and I discussed this down here. Whenever the need arises, one can drill down into the base algorithm to find additional angles to meet new situations by having the difference in the interval between the two pre-existing angles. For example, if you encountered an apex angle of about 41.5 degrees, if you were trying to measure it as close as you could iterate to the solution for the B3 angle, which I have in blue. Now, the B3 apex angle, when we do that, what I've done, I just have the base length between B2 and B4. And that's, of course, B3. And when I figure its apex angle, I get 41.478 degrees, which, of course, as I'm trying to demonstrate, is very, very close to what I had estimated of 41.5 degrees. So that's basically the way you do this. We don't need to do this much in the plant and animal kingdom, but when we get into other areas, we'll need to do this, particularly when we get into things like the street grids and the star constellations. But they all work. Okay, so in order to figure the apex angles of each of these, I have a computer program. You can also do this online if you want yourself. Go to a pyramid calculator online, and you'll be able to figure these apex angles. The unfortunate thing is that most of the uh, 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 calculators online do not do apex angles, and they're important. They do vertex angles, which is a three-dimensional angle. So it's complicated, but I reduce these to 2 dimensions so that I can measure them accurately, and then I expand the work back out to 3 dimensions. Now, uh, supplementary angles. This is the key, as I've mentioned to you, in unlocking so many of these. The supplementary angles are nothing more than 180 minus the apex angle associated with it. So 180 in the first case of B8, 141.569 from 180 gives you 38.43. We've defined that supplementary angle name as S8. So you can begin to, when you start to go through the slides, you'll be able to visualize B8s, S8s, Gs, SGs. That's perhaps the most common combination right there, the G and SG. But that's the way the basic algorithm works. And as I said, we'll be drilling down into it further as we move on in our discussion. Now, an interesting question about supplementary angles. A lot of people have asked me, well, why would the algorithm use supplementary angles? Well, there's a practical problem with the algorithm that has been put together, and that is that there's a practical limit to how long the base length of this pyramid can be. Why is that? Because the slant height of the pyramid triangle is 4.236. We've talked about that in all cases. So the maximum base length that this algorithm can be used for would be 2 times that amount, or 8.572. Anything longer than that, they won't be touching anymore because the base length will be bigger than the sum of the two vertical pieces. So I think that's a big reason why these supplementary angles may be necessary, and we'll certainly see examples of that as we move forward. Now, there's another type of anomaly which is also extremely fascinating once you know what's going on. As a kid, I would always ask my mom and dad why the grapefruit sections weren't symmetrical. Why weren't they the same size? And, I'd get a response like, well, that's the way God wanted it, so that's the way it is. Well, there's a little more to it, maybe, than just that. And I think it has to do with the fact that the algorithm that is used in the universe doesn't have a way of dealing with spherical symmetry. And what we're going to find is that these pieces of grapefruit, they use combinations of these GRS angles best it can to try to come up with an angle or sum that's close to 360 degrees. And we're going to be able to see that. So another obvious example of the simulation in action. And then there's the purely aesthetic golden ratio scaling uses. No one to my mind's eye has ever explained to me where those pyramids come from or where those stripes on the zebras come from. And we're going to see so many examples of these anomalies that can only be explained, like the diamonds on the diamondback rattlesnakes and the stripes on the zebras. Chicken combs, that's going to be fascinating. All of the animal color changes in their fur around their face or their beaks and even on their beaks. It's just amazing. But once you know what you're looking for and you can apply the algorithm, then you see where all of these angles are coming from. Now, before we begin, one last thing that I want to talk about. Along with, I would imagine, most of you in the audience, before I started this research, I thought that I was going to see an infinite variety of scaling angles and growth in the plant and animal kingdoms, and I was just flat wrong. And the reason for that was I'm still, and I'm sure many of you are as well, we're steeped in this idea of local reality. That's the thing that tells us that, the chair we're sitting on is real and that our bodies are real and so forth. So, but one of the things that contemporary brain research demonstrates is that our brains do not provide us with an accurate depiction of reality. Our brain is attempting to dramatically reduce the amount of information we need to process by filtering out things that are unnecessary. And when our brain does that, it has an ability to fill in the blanks that are left from this filtering process by pulling from our perceptual set of past experiences, expectations, and emotions. So already, current research tells us that we're not seeing reality anyway. But in the words of Donald Hoffman, what this means is that we each have a unique headset that creates our own unique version of reality. Now, the ability of the brain to create and embellish upon this limited data that it brings in through this filtration process is essential for people to perceive a much richer environment than actually exists in our 3D world. So, for example, most people believe, and we'll see in the next section, this is wrong, I did too, that the geometry of growth, both expansion and retardation, is highly quantized and is limited solely to the angles found in the algorithm. We're now ready to begin our exploration into the plant kingdom. During my research, I explored 8 major areas of plant growth where golden ratio scaling angles appear, and we'll be going through each of these. That's leaves, gross morphology of the plants and trees themselves, the root systems, branching systems, leaf veins, their fruits, nuts, and flowers. So each of these is a separate unit here within the plant kingdom that we're going to be looking at. The results are just amazing. 100%. Every angle I measured in leaves and all of the other 7 areas had exclusively golden ratio scaling angles. The only exception to that rule is the gross morphology of deciduous trees, where many but not all of the trees demonstrate GRS. It's kind of interesting because the evergreen trees, you don't see much variation. You'll see these angles on the tips of the needles and so forth on evergreens, but you see it clearly in their gross morphology. Harder to see it with deciduous, but very easy to see in the leaf. So anyway, it's just interesting, but they have different manifestations. So again, 100% success. So we're going to start by looking at leaves. Now, what I did in this particular case, I looked at the leaves of all the trees listed in the wikipedia.com list of trees, and 100% of the apex and base angles, which is the terms that are used in botany, of the leaf growth conformed to one of these angles. So you can see there's only 9 angles in total that are used in the entirety of the plant kingdom for all leaves. So pretty amazing. So we're going to start alphabetically. Want to show you a brief diagram before we start. Again, the top of the leaf tip is called the apex, and here at the bottom, that's called the base. We're going to be talking a lot about the veins and the midrib as well. So you can come back and look at this if you need to, but that's really about all you need to know in terms of leaf anatomy at this point. Now this one is out of alphabetical order for a reason. The basswood leaf turns out to be just a phenomenal demonstrating leaf. As you can see at the bottom of the left-hand piece, you can see how there's the leaf is coming kind of to a tip, but really all that you can see visually, at least, without aid of some sort, your mind perceives that this is more or less just a single or a double curve. But what we're going to find as we blow up these is that we find a process that I'm calling leaf growth progression. It goes from one of these angles to the next one in a series, sort of like a progression of chords in a song or something. But we see here on the right-hand side, very hard to see because I had to blow up the picture, but there's a B1 geometry at the very tip of that leaf. As we go up the leaf, we'll see in the left-hand side here the B2 geometry, and then on the right, we can see the B3 geometry, then the B4, then the G, and finally the SG geometry. So this is important because we're going to see this not just in leaves, we're going to see it in architecture, we're going to see it in a lot of different places. So it's antennas of all sorts. So it's a concept to keep in the back of your mind. The other thing that makes the basswood leaf so important, we'll see this in the leaf vein section. This is a gold mine of sacred geometric knowledge, these veins coming off the midrib. Those angles always are one of these golden ratio scaling angles. So now we'll start in alphabetical order and look at a very large number of tree leaves. We'll see here, first start with the acacia. It has the SG geometry, both at the apex and at the base. The alder tree has the Giza geometry at the tip and has the SG geometry going on in its veins. The apple tree, here we can see this progression concept. We see a clear B2 geometry at the very tip, and that doesn't progress through the others. It goes straight to the Giza geometry, and that is what it maintains, for a fair distance down the length of the leaf. Almond tree, B4 and G. Araucaria, B2. Ash tree, B3 and SG. Baobab, B4. And I want you to just look at some of these are so precise that it's hard to, and this one in particular as well, the bay laurel, I got a good close-up of that for the B4 geometry. Beech tree, G and S4. Birch, B4 and G. Black cherry, G and SG. Black gum, B4 and G. Black walnut, B3 and G. Black willow, B2 and B3. Box elder, B4. Brazilian ironwood is the Giza geometry, both at the front and the rear. The buckeye is B4 and G. You can see they're all the same. And you'll get tired of this, I'm sure, after a while. But camphor is B4 and G. You're starting to see patterns here. The front is usually one step in the progression different than the angle in the back. It's usually one degree steeper. Carob, B4. Cassia, B3. Catalpa, G and B7. Cedar, B4. Now here we're not, this is really not a traditional deciduous leaf, but we can see this geometry in the overall geometry of the branch itself. Cedar elm, B4, cherry, G, cherry plum, B4, chestnut, B2 and G, chinaberry, B1. And notice again how that, I didn't do it, but you can see it immediately progresses from the B1 out to probably the B3 or B4 geometry. Cinnamon, B4 and G. Cocoa, B4 and G. Coffee, G. Cork oak, B4. Crabapple, G. Date palm, B2. Dogwood, SG. Douglas fir. Now, here's an evergreen. We can see here these are all looking the same, but we can measure the tips of those, and we'll find the B2 geometry almost all the time. Dragon palm, palm leaves grow with the B2 geometry on the end. Elm leaf, B4 and G. Again, the G is showing up in the veins. Eucalyptus, B4 and SG. Fig tree, Giza, G. Ginseng, B4 and G. Guava, G. If this is starting to look familiar, I apologize, but you need to see this to train your brain to see this. And if you stay with this, you're going to be able to catch these geometries every time you go out in nature from here on out. Gum leaf, B2. Hickory, B4 and G. Holly, B4 and G. Honey locust, G and SG. Horse chestnut, B2 and S4. Jacaranda, G. Japanese maple, B4. Again, juniper. We've got that B1 geometry in the tip. Kauri, B2. Kudzu, SG. Laurel, B4 and G. Lemon, B4 and G. And again, look at the precision of those angles. This can't be anything but spot on. Lychee, B4 and G. Linden, SG. You could see up there, I didn't measure it. It'd get messy, but that's a S1 geometry. Up at the tip, Magnolia, S4 and G. Mango, B1. And again, you'll see this progression from that point on. It's going to be progressing like the box would, to B2s, B3s, and B4s. Maple, B4 and SG. See the SG showing up in the anatomy of the veins. Mulberry, G. Neem, B2. Oak, 3 examples here. B2, B3, and SG. Olive, B4, orange, G and SG. Papaya, B4. Passion fruit, B4 and SG. Pear tree, G. Persimmon, B2. Pistachio, B4 and G. Plain leaf, B2. Plum, B4 and SG. Pomegranate, B4 and G. Poplar, G and B8. Quince, G and SG. Red maple, we can see again, B2, B3, B4, and the B2 and the B4 showing up actually in the leaf veins. Redbud, G and SG. Rubber, SG. Sassafras, B3, G and SG. Spruce, look at the way the branches on the spruce tree are governed as well by these angles. Sumac, B3. Sweet gum, B2. Sycamore, B3. Tamarind, Giza geometry. Tangerine, B2 and B3. Torreya, B2 on the tip. Tulip, B2 and S2. Now, this is the first time we've seen the S2 geometric angle, but again, we're seeing that in conjunction with the B2 base as well. So kind of a clue here that they're using this to maybe make an easier algorithm to calculate. Tupelo tree, Giza, viburnum, B2, walnut, B4, wax myrtle, B2 and B4, white ash, B4 and G, white birch, B4 and G, witch hazel, G, yellowwood, G, and finally Zelkova with a B4. Now I've done many more of these that I didn't include here, but I think you can see at this point that the gross morphology of all of the leaves, the apex and the base, are all going to be controlled by one of these golden ratio scaling geometries. Now we'll move on to the gross morphology area. We're going to first look at evergreen trees. All evergreen trees types, as defined in Wikipedia again, were examined for the presence of golden ratio scaling in their gross morphology. 100% of the trees incorporated one of these GRS angles into its gross morphology. Not very many angles that show up. And this, again, shows you how highly quantized growth is in the plant and animal kingdom. So you only have 4 basic angles, B.5, B1, B2, and B4. So we'll check those out. B.5, we have Italian cypress and the Taylor Eastern red cedar. The B1 geometry, we've got the blue heaven juniper on the left and DeGroote spire arborvitae on the right. Got 3 more B1s, the Graham Blandy boxwood, the skyrocket juniper, and the Spartan juniper. I want to digress here for a minute. You can see these 3 are just so perfectly aligned. It brings into question, and this is for subsequent research, but why is it that there is literally perfection in these, whereas the gross morphology of some of the other trees isn't quite as accurate. So that probably is an indicator that the algorithm also, has a way of using these geometries very precisely and varying them a little bit in the hopes perhaps of keeping somebody like me from figuring this out. But anyway, we'll continue with the B2 geometries. We'll see this Pinsapo fir tree, another juniper tree, Brody eastern cedar, Berkey eastern red cedar, Canadian hemlock, Collimer Norway spruce, arborvitaes, Goldcrest Monterey cypress, a noble fir, another pencil point juniper, another juniper, and a Spartan juniper. Sugar pine, western hemlock, yellow ribbon arborvitae. And again, you're seeing here, these aren't as precise, but you can, once you know what you're looking for and you start to apply it, you can start to see these geometries, even in these trees that aren't quite as precise. The B4 geometry and the deodar cedar and the eastern red cedar, Norwegian spruce and red spruce. Now we'll get to the gross morphology of deciduous trees. And as we said before, a significant number of them do demonstrate this in their gross morphology, but they don't always. And the existence or non-existence of the algorithm in specific areas does not mean that it doesn't exist. So the fact that we'll find it in some of them, and it's again proof that this is a universal scaling algorithm. So again, unlike evergreen trees, the GRS angles that we find in deciduous trees are generally used more as a rough guide rather than precision like we saw earlier with the evergreen trees. So the angles that we find, same old angles, B1, 2, 3, 4, S4, G, and SG. Here's the acacia tree. It has the S4 geometry in its gross morphology. Here's an American tulip with the SG. Basswood tree, we've just looked at its leaves. Well, it has the B4 geometry in its gross morphology. And I actually measured the split in the trunk, and it looks like that's a B1, although we have much better pictures of that coming up. Bay laurel, B4. Birch tree, looks like a G for Giza. Brazilian ironwood is the B8 geometry. Cleveland pear, B4 and SG. Crabapple, SG. Kotsura, B3. Monkey puzzle, B3. Red oak, SG. Sassafras, SG. Sequoia, B2. Tupelo is a G. Then we're going to go on into branching. Now, branching occurs using the same angles as we saw that control leaf growth, B2, B3, B4, G, and SG. And I'll tell you, in terms of diligence, it's a lot harder to find multiple examples of these branchings on one photograph because the branches, I need a direct head-on a photograph in order to properly measure. And so it's oftentimes very difficult to get more than one measurement from tree branching but sometimes I was able to do it. But anyway, we'll start. This is called the Angelita daisy, and you're going to see here the Giza geometry at the base, and we're going to see the next step up, that B4. Again, that concept of progression. We're going to see this happening more and more often. This is another example of this type of progression. Here's the Brazilian ironwood tree, and this is a major branch with the Giza geometry in it. This is called Boneset, B3 and B4 geometries. Here is a case where I was able to get two good photographs, or two good angles on the same photograph. Same thing here with the dogwood. These are branches, and it's a lot easier with branches than it is with the main branches off the trunk. But the dogwood is G and B3. This is a dogwood tree that's in my front yard. I took that picture, so I got a very good angle and perspective on it. That's a B2 geometry in the main trunk branching. This is also from our home. This was a ficus tree we unfortunately left outside, so it died for the winter, but it gave me a perfect opportunity to measure its main branch, and that's a B3. There's a fig tree with some branching with B4, guava with SG, jacaranda with B4, Joshua tree, Giza. And what a beautiful tree it is. Krause's club moss. We're going to see B4 and G. Again, we're going to see these progressions. The linden tree, the main trunk, has a B3 geometry. This palm tree angle, it couldn't be more perfect. But this is a variety of palm, and these are parts of the trunk that have remained after the leaves have fallen off as the tree grows taller. Quince tree, B3, redbud, B3, rubber, B3, sycamore, B3. So you can see that's there. Now, I didn't do a lot more with that because the vein systems that we're going to look at right now are so much more impressive. They're in 2D space, so I can measure them so precisely, and you're just going to be blown away by some of these case studies that are in this section. So again, we're seeing the same angles. We're going to see, however, the addition of the B2.5 and the B3.5. I've had to scale down when I got into these leaf veins, because that's the level of complexity of the model that the model gets into in the leaf veins, unlike the gross morphology, where we didn't get that sophisticated. So I'm going to show you again from our garden. Here's some broccoli leaves I took a picture from our garden. We're going to see B4, S4, and Giza geometries here. And we're going to have some close-ups. So don't think I'm trying to cheat around the edges here, but I'm just trying to give you some ideas of where all of this is coming from. Here's another one that's from our garden, a cabbage leaf vein, B2 and the B3. You see again the B2 is further up, showing that progression that seems to happen in the leaf veins. Here's some cauliflower uh, leaf that was growing in the garden. And here we're going to see for the first time the B5 geometry, which is the 72.36. We had to iterate again between B4 and B6 to get that number, and that's 72.36 degrees. But you see them, and this is true everywhere. Now I found this leaf vein, this is a lettuce leaf vein on the internet, and I used it because the cuts are so precise and the picture quality is so good that this is just a great example for you to see. These, you can't argue with these for lack of precision in the cut. So we've got G, SG, and B8 angles in this leaf vein. Here's a kale leaf vein that I found on the internet, B3, B4, S4, and G. Here's some mint leaves with G and SG geometries. Again, all perfect fits when you blow them up. Um, here's some red oak leaf veins with the Giza geometry. Ripple peperomia veins, B3 and B4. And here's some teak veins, again showing uh, that progression, B4.5, that's at the top, B4, and then B3.5 going down, in progression. There's a tilia leaf diagram, G and SG, tobacco leaf veins, all with the Giza geometry. And now we get to the case studies. These are going to blow you away because of the precision. Um, and the picture quality was so good that I could blow them up very, very well. Now, the first one we're going to look at is called the African mask. And when you first kind of look at this, you say, oh, well, that's kind of symmetrical. And then you look at it a little more, and you think, no, not really. Uh, so I wondered, this was early, in my explorations. I wondered whether I could replicate these each one of these angles with my algorithm. So of course I wouldn't be showing it if it didn't. But here's the African mask. We're going to start on the top right-hand corner. We're going to measure every one of these angles, and we're going to see that they all match up with one of the angles in the algorithm. So African mask, we'll start at the top right again, B4, B3, B4.5, B6. Very interesting thing, and this is a digression, but you notice that the B6 angle is virtually identical to a 90-degree angle. And I think that's one of the reasons that this algorithm was chosen, because you'd have a 90-degree angle in the algorithm that you could choose without having to complicate the algorithm very much. And it wouldn't be perceptible to the human eye, to the naked eye. So that's a B6. Now further down, the Giza geometry, the B4 geometry, B3.5. See how they were getting bigger? Now they're starting to scale back down. The center of the African mask, that hole, is a B4 geometry. Then we start on the top left, B2.5, B3.5, B4.5, G, G, B5, B4.5, and Giza. So every one of these angles matched up to what I had wanted to accomplish and to show you. Now we're going to look back at that basswood leaf that we looked at again for the progression at the base, of the growth of the leaf at the tip. But we're going to see the same thing. We're going to do the exact same idea. We're going to start on the right side. We're going to measure all these angles, and we're going to find that each and every one of them shows up from the algorithm. So we're starting again. To go back, there's the hole in the middle. We're starting at the top right. We'll start with a B1 geometry. Then we've got a B4. Now another B4, a Giza, a B3.5, and a B4. Now going along the right side, we're going to go down a bit. B4, B3, 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 B3. Now moving down the middle, down the spine, B4, 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 B3, B3. Now on the left side, B4, 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 B3, B3, and B3. And then moving along to the left side, we'll see a B4, another B4, and another B4. The next case study is the philodendron. I found this on Bing Images, and I looked at it and I said, oh my God, if there's ever anything that's going to be perfect for demonstrating these, it's this leaf, because these leaves, the veins are so straight. This is such a wonderful example. So we're going to see the same thing here. I'm going to start at the top right. We're going to start with a B2 geometry in the veins. Then we're going to go to B3, B3.5, another B3.5, and I want to point out here, see how it's starting to angle off. It's only, it's appropriate at the beginning, but it's starting to veer off. But that's the way that it takes just a limited number of angles and creates this perception of infinite diversity in our reality. Here's another B4, another B4, B3, coming back down again, B2, and B1. Now we'll do the same thing on the other side. B2, B2 and a half, B3, B3, B3 and a half, B3 and a half, B3, B2, and B1. Now, one thing that you may not have realized, but you'll see it here on these veins. First, let me show you. It looks as though the main part of the vein here in the back is scaled with the B.125 geometry as well. So, so much to see here. This angle is a little challenging because my precision goes down when I try to measure something this precisely that is this thin, but it seems to match. Finally, we're going to look at Swiss chard. Same ideas. This is a much more random leaf, so we're going to see these geometries in all different places, and it's not quite as clear. But I want to show you these Swiss chard geometries. B2, B4, B4, B2, B1.75, B3, B4, B3, B8, G for Giza, B4, B3, B3.5, B3, B4, B4, and B3, and another B3. And it looks to be scaling, its stem with the B.25 geometry rather than the B.125 geometry that we saw in the philodendron. But these are just amazing examples, and I can guarantee you that there's no one in the world of biology who has figured this out yet. So this is going to be major new stuff for the biological sciences. All right, let's move on to roots and tubers. All roots and tubers measured use these angles. Same old angles, B1, B2, B3, B4, and G. It's the same culprits. Alaskan peep root tip, B4. With my biology degree, my botany project was determining the onset of mitosis and the mitotic index in the Alaskan pea. But my expensive Ivy League biology education didn't tell me anything about what I'm showing you today. Burdock, a tuber, B1. Carrots, B1 geometry. We can see a little bit of progression down here. This is obviously a different geometry, but the main body is scaled in B1. Cassava, B2. Corn root tip, B2. Ginseng, B1. Mashua, B3. This is a picture I found of oak tree roots. Now, that's a drawing, so take it for what it's worth, but it looks as though the diagram is indicating that the roots underground use these very same geometric angles as well. Oka, we've got two varieties here, B2 and G. Onion root tip, B2. Parsley, B1. Parsnip, B1. Ryegrass seed tip, B4. Sugar beet, B2. Sweet potato, B4. Wasabi, B2. Wheat root tip, B3. And yucca, B1. So we're seeing it in all of the root systems and the tubers and so forth. Now we're going to go and look at plants. These are, as opposed to trees, there's no real hard and fast difference, except that plants usually don't grow as tall, don't grow for as long, they die faster. So there are those qualitative differences, but you'll recognize many of these plants as being exotic household plants as well. So again, we're seeing the same set of geometries. We've got a few somewhat out of ordinary, B.5, B3.5, but the rest of it is, again, just the same old angles that we've seen before. So here's the African spear plant. Its tip grows with the B2 geometry. Here's the agave with the G geometry. Alocasia, B3. Alocasia stingray, B4. I know if you're like me, till I measured these, I thought these were so unique and interesting. Unfortunately, they're just part of the algorithm. Aloe, the aloe roots, B.5. Aloe, B4. Amaranth, G. Bamboo, B1. Begonia, B3.5. Begonia maculata, B2. Blueberry leaves, G. Caladium, B3 and G. Calathea, SG. Cannabis, B1 at the tip and G in the veins. Cardamom, B4. Cast iron plant, B3. Catnip, B2. Chinese money plant, SG. Christmas cactus, this is from our house as well. You see the flower petal is B2, and the Christmas cactus section there has the SG geometry. Clover, 3-leaf and 4-leaf clovers, B6 and B7 geometries. Cone plant, G. Coral cactus, G. Curry, B2. Dieffenbachia, SG. You can see I could have measured again that tip up there. That would have been probably an S1, or excuse me, a B1, forgive me. Eastern prickly pear cactus, B4. Edamame, yeah, Giza. Fiddle leaf fig, B4. Flapjack, Giza. Fuji panfall, I love this one. It's the SG geometry. If you've ever wondered, that's how it gets its geometry. Gasteria, B2. Heartleaf philodendron, B2. Ivory halo dogwood, B4. Jade plant, look at how perfect these angles are, B4. Lace aloe, B3. Lamb's ear, B4 and G, again from our garden. Money tree from our house, B2. Oregano, B3. Paddle plant, SG. Peace lily, got the Giza geometry going. Plantain, G. Rex begonia, B4. Shark jaws, B4. Snake plant, B4. Spider plant, B2. Spiral ginger, B1. Star cactus, S4 and G. You just don't know where you're going to find these, but they're everywhere. String of buttons, G. Swiss cheese, this is B3 with B4 as well, angles. Taro, B3 and B4. Urn plant, B2 and B3. Venus flytrap, Giza. Water lily, B1, B2, B3, and B4. Now look at this and tell me, how can this happen? I never knew this until I started measuring these. But this was a picture from the internet, and sure enough, each one of these water lilies was demonstrating a different one of these geometries. The yucca plant, SG. Now we'll look at ferns. Ferns are a group of vascular plants that reproduce via spores, and they don't have seeds or flowers. So they're sort of a unique, plant in that regard. Ferns demonstrate golden ratio scaling at a couple of different levels of organization, but you don't see that many angles in the ferns. You see B1, B2, and Giza. So now here's a Boston fern. The gross morphology of the leaves is B2. Here's a broadbeach fern. Again, gross morphology of with Giza. Here's a coastal wood fern, same thing, B2. Now here's a foxtail. This is a different kind of fern, but you'll see it. It grows obviously differently, but it has the B2 geometry. A hard fern uses the B1 geometry to scale, and the mosquito fern has the Giza geometry in the base. The staghorn fern uses the Giza geometry from its growth out of the ground. Now we'll look at ivy. Ivy is very much like other leaves. It's very, very precise. We see these angles, B2, S2, B4, G, and SG, same old angles. So Baltic ivy is G. We can't see that well. That's down at the base. The SGs and then the B4 is in the leaf veins, as is the SG in the veins, as well as the geometry of one of the sides of the leaf. Boston ivy, again, we're going to see the B4 and G geometries in the leaf veins. English ivy, Giza and B4. Variegated English ivy, we've got the B4 down at the base, and then we have the S2 geometry in the veins. Irish ivy, Giza and SG. One more time, we see this. It's so common in nature. Next, we're going to look at berries. Berries are, small, pulpy, and edible fruit, but berries are not going to have, except in rare occasions, are not going to have real precise angles, but they are there if we, can use our imagination. A lot of times, they're very obvious as well, but we don't see very much variability here. We see the B2, B4, and Giza geometry. So the barberry has a B4 geometry, black raspberry, B2, and as I say, these are, some of these aren't as precise. Now, here's a very precise measurement. This is actually where the berry connects to the plant, and there are 4 of these on each blueberry. If you've never noticed them, go check them out the next time. They have a Giza geometry. And here's another picture from a different angle of that geometry in the blueberry. Boysenberry, B2, capers, Giza, and I missed that's a B4 as well. Goji, G and B2, Loganberry, B2, mulberry, B2. Here we see some precise ones. The pineberry is very precise, B4 geometry, as is the salmonberry. We see that, and we see the supplement for the B4 geometry on the other end of the berry. Strawberry is a very precise Giza geometry. The tayberry is a B4. Nuts, however, are such a great example. Every one of these nuts has one of these geometric angles in the tip. And what I did for methodology, I looked up all of the nuts in Wikipedia, and they all contained at least one of these GRS angles, S2, B4, S4, G, and SG. Same angles. All right, here's an acorn. The S2 geometry is at the top, and at the tip down here, we see the B4 geometry. Perfect match. Now we're going to look at all of these nut tips, and we're going to see that their angle of growth is all regulated by these GRS angles. Almond, B4, Baru, G, Beech, B4, Blanco almond, B4, Bunya, G, Canarium, B4 and G, Cashew, SG, Chestnut, S2 and S4. Now, there are three of these that look virtually identical, and you'll see them here in a few minutes, but they all have this same geometric angle, and they all look pretty much the same. Now, the Deca is a B4, but here we have the filbert I was mentioning. Here's another example of that geometry. These look virtually identical and have the same geometric angles. Fritz almond, G, ginkgo, G, green almond, G, hazelnut, the last of these three, S2 and S4 again. Korajong seed pod. I'm not measuring the seeds here, but the geometry of the pods that they grow in, and that has the Giza geometry. Macadamia nut, B7 geometry. Malabar chestnut, B4. Marcona almond, B4. Mission almond, B4. Monkey puzzle nut, B2. Pecan, look at that. Perfect Giza on one end and the S4 on the other. Peely bean, B4, or nut, excuse me. Pine cone, it's not a nut per se, but I put it in here. You'll see all of these geometric angles showing up in that pine cone, B4, G, and B8. Pine nut, B4 and G. Saba, B4. And then fruits. We'll get into fruits now. Fruits angles include B2, B3, B4, same old angles, G, SG, and one or two B7s, which are somewhat unique. All right, if we think about apples, every time you look at the tip of an apple, that's going to have the Giza geometry at the top. Look at the geometry of the seed and the hole for the apricot, and that's the Giza geometry. Look at the scaling of the gross morphology of the avocado. It's using the B2. Cantaloupe is using B3. Carambola, B4. Cherimoya, B4. Cherry, once again, we see that the G geometry. Durian has these B2 geometric like pyramids all over it. Elephant fruit has the B4. Fiahoa is G. Grapes are B2. Guava, G. Kiwi, B2 and B4. You see these segments. It's a little hard to see, but there's segments that are defined, little pods inside the kiwi, which have these geometric angles as well. This is Hala. You're going to see, even though these are not symmetrical, you're seeing these angles showing up. The G and the B7, I could have done more, but um, we'll talk about the relevance of that in just a moment. But you're going to be seeing that these angles show up even when things aren't symmetrical. Horn melon, B4. Jackfruit, G. Jungle sop, B4. Natural plum, G. Pear, B4. Peach, Giza. Pineberry, SG. Look at that, those angles. We'll see those in many other places, like scales on lizards and lots of other places. Persimmons, B4. Pineapple, G, SG, and B2. Quince, SG. Watermelon, B4. Now we're going to get to the anomalies that I had mentioned in the introduction. And these are asymmetrical fruits. As it turns out, certain fruits are obvious anomalies that point to simulation theory, as the slices of fruit contained inside them are not symmetrical. Nature has this predilection to try to do things symmetrically, and when you don't see symmetry, that's when you need to raise your hand and ask a question. Why is that? Well, to begin with, before I did my research, I did some research on this topic, and I saw that the Max Planck Institute in Germany had already discovered that 7-sided, 9-sided, and 11-sided symmetrical structures literally do not exist in nature, a sign that the simulation may not be robust enough to create these objects. What's actually happening, we're going to do this with several examples, we're going to find that the algorithm is trying to pick combinations of these GRS angles, and they put them in to the mix to try to come up with a sum that sums as closely as possible to 360 degrees. So this is further evidence, and you won't understand it until you see it. But here's the 10-section grapefruit that we're going to explore today. And if you look at it, you can see automatically that they're not the same size. But when we go to measure each of those 10 sides, here's what we find. We find that there are 2 B2 geometries, there are 4 B2.5 geometries, and 4 B3 geometries in the mix in this 10-piece grapefruit. Clearly, if it had the ability, all it would have to do would be to divide 360 by 10, and it would have 10 36-degree angles for slices, but it doesn't do that. So what does that tell us? It tells us that there's a very limited algorithm at work here in nature to scale spherical objects. So just to demonstrate this, we'll start at the top here. This is a B3 geometry, as you can see. And this is another B3. Now the next one turns out to be a B2 geometry, and the next one turns out to be a B3. What's happening here, as you can see, let's go back a picture. You can see how that angle that whole slice has been pushed out a ways because you can't jam all of these angles into a perfect circle and make this work. Now here's a B3 geometry again at the beginning, but look at how it fans out as it gets away from the center, where it seems as though this algorithm has the most control. Now we've got a B2, B2.5, 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 and B2.5. So, we've seen that it's picked these, it's put them together in some fashion. It was very close to 360, but not quite. Now, I did the same thing with an orange. This orange has 9 sections. And of course, once again, if we could figure out, it actually has 9 and change. If you look here at about uh, 8 o'clock on the dial, you'll see this little sliver here. So I'm calling it 9, but it's really 10, but it's a mess. So I did the same kind of an analysis here, and we've got one mess that doesn't make sense, but the rest of the angles are we've got one B 2.5 and 7 B3s. So out of 9, and we have a mystery section. So just to go through this again, orange B3, got another B3, another B3, another B3. Now we've got a 2.5, another B3. And here again, see how this thing pushes out? At the beginning, it's a B3. But here, these next two sections, virtually impossible to figure out what those angles are. But it's just a mishmash that ends up making a very non-symmetrical citrus fruit. So you can see the rest. Same thing with the kumquat. Uh, we've got one B4, one B5, and it looks like three geezes, which gets us very close to the 360 degree that we would need. And oops, that's actually 5 sections. But we'll see the kumquat here. First section is a G, another G, B4, Giza again, and a B5. So we'll just, I'm not going to do any more of those, but we'll see the lemons work the same way. We've got a B3 and a B4 geometry in the lemon. We got a B2 and a B3 in the lime. This is a mangosteen, another type of circular fruit, spherical fruit. And it has 5 sides, and none of this seems to work, but on these 3 large pieces, it's using the B4, G, and GS geometries, but they're getting all squished around and messy. Satsuma, same thing, B3 and B4. But moving away from anomalies, we've now come to the section on vegetables. If you ever wanted to see lots of symmetry, this is a great place to see it. And vegetables use these extensively. B.5, B1, 1.5, 2, 3, 4, S4G, and SG. So we'll start with acorn squash. Acorn squash has the SG geometry controlling its apex. The artichoke, we see each of these artichoke heart or leaves has the B4 and G geometries. Asparagus tips all have the B2 geometry. Bamboo shoot scales with the B.5. Banana squash, B2. Beets, SG. Bok choy stalks, G. And what you're looking at here, this is a piece of bok choy in the background, but this is a stalk that is divided in half, just like those ironwood trees and everything else. Perfect Giza geometry in that separation and branching. Broccoli flower, B4. Broccoli, B2 and B3. Brussels sprouts, B4 and S4. Again, seeing these supplements showing up together, it's just amazing, and I can't explain it other than through an algorithm. Here's some scaling and progression in the leaves in the veins of cabbage. Cayenne pepper, B1. Chard, perfect B2 geometry growing out of the ground. Chili peppers, scale at a 0.5. Collard greens, B2. Corn, B2. Daikon, B2. Eggplant, G. Indi, perfect B2 angle. Here's another one of these anomalies. This time it's with garlic, but we're seeing this spherical object once again that can't seem to come up with a way to scale symmetrically. So once again, in the 10 section garlic, I'm showing you that we have a B4, B4 angles here that shouldn't be there if this were symmetrical and there was a scaling algorithm to achieve it. Green pepper, B4. Jalapeno, B2. Kale, B4. Leeks, once again, the branching, perfect Giza angle, G. Nopales, G. Okra, SG. And on B2. Now, here's a case study I did on the onion. And I think this is fascinating. I started it, and it continued to work, just like the branching in the leaf veins that we saw earlier. So what we're going to do, we're going to start here, and we're going to see the B3 geometry in this leaf. Now, or in this section. Now we scale upward, and we go one further out. We're at the B4 geometry. We stick with the next level up with the B4, higher up on the tip of the onion. And then we move to the Giza geometry. And once again, we see the Giza geometry on top in the next section of the onion. So we move to the bottom. We start there. We continue with the Giza geometry. Another Giza geometry. Then we move to the SG, the S4, and the B8 geometries. So this is pretty phenomenal. I'd love to have the ability to do these with even more precise equipment, but I can tell you that this just fits the normal, standard. Everything is fitting into the algorithm. Paprika, B3. Poblano pepper, B3. Pumpkin, S4. Radicchio, B1.5. Radish, B2. Red leaf lettuce, G. Red pepper, B4. Romanesco broccoli, what a perfect fit, G. Rutabaga, B4. Savoy cabbage, who would have known, why would anybody think that these angles might all be programmed, but the Savoy cabbage, B3 and SG. Shallot, B4 and G. Turnip, G. Now mushrooms and fungi. We know the mushrooms and fungi, are all around us. I love eating mushrooms, but I never knew that they all had sacred geometry in them until I started doing this research. But the angles used here, B2, 3, 4, S4, G, B7, and SG. So this is the Amanita muscaria, or magic mushroom. The mushroom cap has a SG geometry. This is called Acerorubra. It has the Giza geometry. The black trumpet has the B1 geometry. The chanterelle has the SG geometry. Corioactus, B3. Clathrus archeri, B4. And now for another anomaly. This is another Clathrus. This is called the Clathrus ruber, and it has 7 sides, as you can see. Done the same analysis here. We have looks like 2 S3.5s, 4 S4s, and then a mystery angle to finish things out. So I'm going to go through here. This is the S4 geometry, starting from the top and going clockwise. Then we have an S3.5, an S4, and then this is the mystery angle. Very hard to define, and it's obviously not symmetrical. So we see that, then we move on to the S4, S3.5, and finally another S4. So again, we're seeing these angles showing up, and then it seems like the algorithm just sort of, fills in the blank for the balance. Coprinus comatus, B2. A cup fungi, B4. Cyathus striatus, B2. Dermatophyte skin fungus. Now this is a fungus that grows on human skin, and it can be somewhat problematic, but we see that the branching in this skin fungus uses these geometric angles as well. specifically the B3 and the B4. Geastrum minimum, B3. Hydnellum pecki, B4. Hope I'm getting these right. Lepotia, B4. Laratiomyces, S4. Morel mushroom, B2. Mycena chloropus, this is the one that glows, is G. Phallus induciatus, B4. Porcelain mushroom, S4. Porcini mushrooms, B3. Puffball, B8. Rusula, S4. Tiny golden, B4. Yellow, B7. Now we'll do a brief study of sea plants as well. There's not a lot here, but I did look at them fairly extensively, and we're going to see these same angles. Caulerpa, G. A fucus plant has the B4. Great Star has the SG geometry. Another one of these anomalies. This is a 1, 2, 3, 4, 5, 6-sided. Yep, algae, and it uses S4, SG, B7, and B8. I didn't go through this again this time, but obviously there's an angle that's not part of it, and you always are going to see that whenever you have some sort of a polyhedron coming together. You're going to find one angle that's not going to match up, because they all have to, match up in total to whatever the number of degrees in the polygon need to be. Halimeda, S4. Kelp has the Giza geometry at the tip. Here's a mermaid's fan, B7. Red algae, B4 geometry again in the branching. Now we'll look at sea coral. Sea coral has these, and they use the B3, B4, G, and SG. Same angles as we keep seeing all the time. So here's a black sea rod coral that uses the SG geometry. Here's a finger coral, B2. Here's an anomaly. I'm calling it an anomaly. This is called a groove brain. And this has the B3, Giza, and SG geometries in what looks to be just a purely random act. But this is obviously part of an algorithmic structure. The ivory bush, B3. Mushroom coral, B8. Organ pipe, B4. Pillar, B2. Pulsing xenia, B4. Purple sea fan, B3. Soft coral, B4. Staghorn, Giza. Now we're going to get to the very last segment of the plant section. We're going to be looking, plants and trees, plant kingdom, at flowers. Flowers are generally the reproductive structures of flowering plants, and they're generally structured in 4 circular levels called whorls around the end of a stalk. Well, this is going to blow you away, but I did look at every angle of every flower on the Wikipedia website, and I found many more even beyond that. But every angle is from the algorithm. All, or virtually all of them, are from, again, the same basic set: B1, B2, B3, B4, S4, G, and SG. So I think what I'm going to do, you've heard me talk enough. I'm going to be quiet through this segment, and I'm just going to let you guys enjoy a little background music while you look at all of these flowers. I do want to interrupt your music at this point to talk about the dogwood leaves. This again, this is coming right from our front yard, and this was in full bloom. And I think this is a great one to just talk about for a moment. All of the sacred geometric angles that are showing up in this are just phenomenal. You see, uh, actually, you have a 4-leaf setup here, but you have 2 leaves that are on top of another 2 that are at 90-degree angles from them. Well, we see that the tip of the upper ones use the B4 geometry, but the ones that are below the tip is the G, and then we're going to see the S4 geometry right here on the angles between these 2 leaves, and then we're going to see the SG geometry at the base of the leaf. So and Giza here between these 2 angles, there is sacred geometry with these everywhere. This ends our exploration of the plant kingdom. Um, and the summary of results is as follows. Based on 100% success rate on thousands of measurements, and that's literally what my results have been, the geometry of plant growth is highly quantized and is controlled using one or more of the GRS angles found in the algorithm. This is a significant discovery that I believe deserves serious consideration from the botanical sciences, and as it will when we look at the animal kingdom in the next section. This is not information that is available in the public domain. So uh, if there's anyone out there, and I'll say this again at the end of the animal kingdom section, who works in the biological sciences, can help to get this out into academia, there is so much research to be done here. Now that we know that we have a simulation in terms of new research that can be done to explain both the growth of plants and animals, but also their interaction with the algorithm. So this is huge stuff, I think, and I want to see this get into to biology. The fact that growth is controlled by only a limited number of angles is only explainable by a computer algorithm or simulation. Once again, we're no longer dealing with local reality science here. This is the beginning of the non-local science that we need to get into our academics. And the fact that finally that numerous fruits do not contain internal symmetry, coupled with the fact that we've already found out from the Max Planck Institute that 7, 9, 11-sided symmetrical shapes do not occur in nature. And we saw all of those strange anomalies. These are all further demonstrations that the algorithm discovered may be the only one available. Now that we've finished our investigation of the plant kingdom, it's time to move on to the animal kingdom. Now, in general, the angles that we're going to find in the animal kingdom are just exactly the same ones that we found in the plant kingdom. And we're going to find them in basically the same places. If we look at insects, we're going to find that their faces, their body structures, their antennas, all of these fundamental aspects of their morphology all follow golden ratio scaling angles. So we're going to go through all of these different examples in the animal kingdom. A couple of things that you're going to find. First of all, as you go up the complexity ladder, it's not that it becomes increasingly difficult to find, but it is more difficult to find, say, in the superstructure of the human body visibly than it is in the antennas of or the horns of an animal, which all have these. But we're going to find these angles in different places. But in general, what we're going to find is that you'll see this very easily in the smaller animals, less complex. We're even going to start with single cell organisms named diatoms, and we're going to see these angles there as well. So one of the critical differences, however, is the existence of this algorithm for purposes of pure aesthetics. So if you've ever wondered, how come we find all of these weird triangles on tortoises and turtles, or all these geometric diagrams on mollusk shells and so forth? And have you ever wondered, how did those get there? Nature didn't do that through evolution. So we're going to find that all of these angles that are found in these aesthetic purposes are using these GRS geometry angles as well. So let's get started. I'm going to show you, we're going to start now with the introduction page, and then we'll move on to diatoms. So again, to summarize, the animal kingdom has numerous examples of golden ratio scaling being used for purely aesthetic purposes. We're going to focus on that. I mentioned earlier, these are great examples to show you that we live in a simulation. All the horns and antennas of animals and insects have these geometric angles, and they are so perfect. You just can't deny the fact that this is done via an algorithm. Now, also, many human organs, bones, muscles, and other body parts have these angles. A little harder to see because we're a more complex organism, but they're there, and we're going to go through those in great detail. Finally, and I think this is significant, human sensory receptors, including our DNA, have gross morphology of one of these GRS angles as well. So we're not going to get into that in this documentary, but I think that that's going to be highly significant for purposes of future research. Now, the first section that I'd like to go over is diatoms. Diatoms are a type of algae found in the oceans, waterways, and soils of the world. Diatoms make up a significant portion of the Earth's biomass. They generate up to 20 to 50% of the oxygen produced on the planet each year, take in 6.7 billion tons of silicon from the waters, and constitute nearly half of the organic material found in the ocean. So these are highly significant, and I thought it was important to demonstrate that these angles even show up in single cell organisms. So these don't necessarily have names, but we're going to just go through a couple of these examples to show you. This is a picture of a diatom with the S1 geometry. You see these four lines, two of them are jutted out at an angle, and those angles equate to the S1 angle. Here's a diatom with the B3 geometry, the geometry, another G. Here's one with B3. I think it's fascinating to see the complexity, structural complexity of these single cell organisms. But they seem to be guided 100% by these angles that we found in this algorithm. Here's a B2. And notice the precision as well. Once again, very, very precise use of these. And we're seeing, the same basic angles that we saw in the plant kingdom. Moving on to insects. Insects are built for efficiency. They're small. So it's not surprising to see these angles in both the micro and macro aspects of their anatomy. So we've got a big selection of insects to look at here. The primary angles we're going to find are B.5, S1, B2, S2, B3, B4, S4, G, SG, and B8. So we'll get started. There's some excellent photography, close-ups of insects on the internet. So I have a great opportunity here to show you these precise geometric angles in insects. So here we have an example of an ant with the G geometry on the bottom and the B7 on top. Probably could have measured those little horns up there as well, but I didn't want to clutter the photograph. Here's an aphid. Here we see very similar to the leaves. You're going to see one geometry in the rear and another geometry, in the front. But here we have the G and the B3 geometries, literally defining the gross morphology of aphids. And next we have the Apis mellifera with the B5 geometry. This is the tail end of a bee, which has the SG geometry. Here's the face of a beetle, with the top angle being the S4 geometry and angle, and the base, the bottom part, is the SG. This is a blue bottle fly. I mean, these are the kinds of pictures that tell you this has to be simulated, because these fly eyes are angled precisely, in this case, with the G geometry. We're going to see this in some other cases as well. Here's a little mini case study I found. I found this particular insect, the Bocydium globulare, and I said, gee, I wonder if those horns, similar to the uh, deer antler and horns that we're going to see later, if they have these geometric angles as well. And sure enough, the central angle there is the S4. Then the next two are B4s, and then finally a B3 for the final angle of those horns. So clearly being used there as well. This is book lice with the B2 and B4 geometries defining their gross morphology. Here's a caddisfly. You can see the wings have the B3 geometry. There's the Giza geometry down at the base and the SG geometry at the top. Here's a cicada, and we see the G and the SG geometries. The G geometry is defining the slope of the eyes on the insect, and the SG is located right there. So here's a common fruit fly. Once again, we're going to see these eyes being defined geometrically. The eyes are defined by the SG geometry. And up top, we're going to see the antenna are using the S4 geometry, and then there are some little claws, I guess, up front here that have the Giza geometry. So clear sacred geometry here as well. Now here's a classic example. This is a cockroach. Look at all of these examples. We've got the B4 in the rear anatomy of the cockroach. Then we see this triangular shape here as well that has the B4 geometry. We've got the B2 geometry defining the gross morphology as we move forward. And then we see the 123.653, the S4 geometry right here. So tons of examples of this here in this simple cockroach. Here's a cricket. The geometry of the legs is B2.5, and the head uses the S4 geometry. Damselfly, B4, B8, and S1. Here's some creatures I had never known about before, but these are called this one is a deep ocean worm. We see B4 and S4 in its gross morphology, and then I also found this deep sea worm, which has the S2 and B3. Many more angles I could have measured here, including these little antenna things up top, but chose not to do that to keep it from getting cluttered. Digger wasp, B4 and B5.5. Again, the angle of the wings being defined by GRS. Here's a dragonfly with the B4 up front and the S1 and S2 angles defining the wings. And here's an interesting depiction of the dragonfly's eyes, here using the B6.25. We've talked about this before, that in the context of simulation, one reason why this angle is so important is because it's about 95 degrees. So we're going to see this angle showing up in other contexts as we move forward. Here's another anomaly with these angles in just hiding in plain sight. This is the giant water bug. We've got the Giza geometry up front. We've got the B4 in the back. And we have two Giza geometries showing up in the body on the back of the water bug. Grasshopper, B2 in the front and the rear. Here in the front, we see a purely aesthetic purpose, defining the separation between the yellow and the blue colors. And in the back, we're seeing it in the gross morphology. Green fly, B.25, defines the wings. Here's a green stink bug. This almost looks like it was done with a computer algorithm to me, but very precise angles at the front. We've got the S4 geometry there. We've got the B4. Again, we see B4 and S4. We see these supplements so often together. And then we see the Giza geometry defining the rear side of the stink bug. Here's a head louse, B3 geometry in the middle, and then the B4 geometry defining the contour of the head. Here's some insect eyes. These were wonderful photographs I found on the internet. I could not find which species of insects these came from. However, I wanted to show them to you. Here's an insect eye with a perfect Giza geometry. Uh, and then here's another insect eye, again, using these progressions. We see the B3 geometry, which uh, morphs into the B4 geometry higher up. So these cannot be anything but computer generated algorithms. Ladybug, we'll see B3 and S4. B3 defining the gross morphology in the front, and the S4 defining the wings. Lice again, B3 and B4. A locust, look at the B.5 scaling in the gross anatomy and the SG geometry in the head. Praying mantis, Giza and S2. Mayfly, B2. Mosquito, you see the B2 in the rear, and then this is nothing more than an aesthetics feature, but we've got the Giza geometry there as well. Nepidae, again, gross morphologies using B2 and B4. Here's an orchid mantis, a variation on the praying mantis with the B4 and B5 geometries. Here's a red bug. Look at this. These are so precise. You can't tell me these aren't done with a computer generation algorithm. But B3 and B4 geometry, sandfly, B2 and B3, scorpion fly, Giza, and B2. The B2 is defining the angles of the wings, and the Giza is defining the geometry of the antennas. Silverfish, B1 and B4. Snakefly, we see Giza in the front, and then we see S4 and G in the wings. The gross morphology of the face of the termite is defined by the B3 geometry. The thrip contains B4, SG, and B2. Tick's gross morphology is defined by the B3 geometry, and we see the B4 geometry in the face of the wasp. So we've seen a lot of examples. I could have done a lot more, but it's clear that these insects, including the weevil, B2 and G, and the yellow jacket, they all have golden ratio scaling geometries. Now, the next section, we want to cover our insect antennas. We just saw how important these angles were in gross morphology, but this is going to be a kind of a case study, a deep dive into antennas to show you how precisely and how perfectly each and every insect antenna adheres to one of these geometric angles. So we'll start with the American copper butterfly. I've got a whole section on butterflies and moths that we'll be seeing later, but sometimes I wasn't able to get the antennas measured because I was measuring other angles, but I wanted to let you know all of the butterflies and show this via example have these geometric angles as well. Here's the ant with the SG geometry for its antenna. Here are aphids, B3, bean weevil, SG, and I want you to focus on how precise these geometries are and ask yourself, I know this is bringing up cognitive dissonance for a lot of you, but how precisely these are. And consider what are the chances that this could be done without an algorithm. They're virtually non-existent. Redbug, G, bedbug, excuse me. Bees, S4. Beetle, B3. And see here, it starts with the B3 geometry and then it converts to the B8. So that's why I picked, this diagram to demonstrate that. Brown beetle, G. Book louse, G. Butterfly moth. Look at this. I mean, there's B4 on the ends. We've got the Giza geometry defining the antennas, and then we've got the S4 geometry defining the connection to the moth. Caddisfly, B3. Cicada, G. Perfect match. Cockroach, B4. Common fruit fly, B4. Cricket, G. Damselfly, B2. Digger wasp, 6.25. Seeing that angle again, once again tells me that this is a simulation because it's about 95 degrees. Dragonfly, again, B625. Two in a row that we found that way. Dung beetle, same thing, B6.25. Earwig, B4. Firefly, B4. Flea, SG. Termite, G. Giant water bug, B4. Grasshopper, B4. Greenfly, B2. Our friend the green stink bug, perfect Giza geometry in the antennas. Hercules moth, another moth, B2 in the geometry of the antennas. Ladybug, SG. Lice, SG. Lobster, G. Locust, B3. Maggot, G. Mantis, G. Mayfly, G. Mole cricket, SG. Mosquito, B2. Question mark moth, B2. Redbug, B3. Sand flea, B4. This is just phenomenal. Scarab, G. Scorpion fly, G. Silkworm moth, SG. Silverfish, B4. Snakefly, B4. Termite, G. Thrip, B4. Walking stick, B3. Wasp, SG. Weevil, B4. Zebra long-winged butterfly, G. So every single one of these ended up with one of these GRS geometries with a perfect fit. No chance that this is done by accident. Moving on now to mollusks. This is another example where it's just hard to fathom that every one of the mollusks fits, the angles on the mollusks fit within these geometric angles. And it's not that many angles that we have to deal with, as we see B1, B2, S2, B2.5, B3, B3.5, B4, G, and B7. We're going to start with the Abas cone, which has the B2.5 geometry. That's down at the base, 34.25 degrees. Again, in this case, we had to iterate between the B2 and the B3 geometry to get the B2.5, but it matches perfectly. And then at the top, we see the Giza geometry perfectly fitting the top of the cone as well. Now here's another cone, the Abbott's cone, and we're going to see the same B2.5 geometry on the base, but at the top, again, rather than the Giza geometry of 76, we see the supplement angle of 103.655, perfect fit. Altrina, B2, American auger, this is, again, one of these examples of progression. The main body of the auger is the B1 geometry. That's just the angle. But at the tip, it's the B2 geometry. Once again, seeing this progression concept in action. American star, B4. Angel wing, isn't this beautiful? Giza, Arabian tibia. Look at this. Isn't this a beautiful shell? B5, B.5 on the tip, and B2 in the main body of the shell. Aerodwarf Titan, B2. Here's just a plain otter shell, B1. I'm going to try to say this, Arysiacus. We're going to see the B2 geometry in the main body, and we're going to have the SG geometry on top. Austral cone, B2 base, and B4 this time in the top of the cone. Here's another interesting phenomenon with mollusks. Uh, these types of cones show progression with even internally within the same portion of the shell. If we look at the picture on the left, we see that, let's call that the front view of the shell, has a B2.5 geometry, but when you turn that shell over and measure that extra section that we see here on the right side in the front view, we get a B3 geometry. This can't be an accident. Banded tulip, B4. Beaded periwinkle, B4. Bucinidae, B3. Bumblebee snail, B4, all perfect matches. Bermuda cone, again, B2.5. And in this case, we switched it up a little bit and got the B5 on the top of the cone. Butterfly cone, we're showing again, B2 and B2.5. And I just have to say, parenthetically, doesn't this really this shell look like it's some kind of computer generated algorithm that produced this beauty on the shell. Caribbean blacktop, G. And these are Chitonidae. This is one of my favorite examples of the architect of the simulation showing off. We're going to see three examples of these. You can see this one's red and this one's a kind of a lighter color. But what we're going to find, each one of them has 6 triangular shapes, and each and every one of them is a match to these angles. So in this case, however, in the gold example, we have 1 B3 geometry, 2 B4s, and 3 geeses. Now in the red version, we have 1 B3, 1 B4, and 4 geeses. And then finally, in the third variation, we have 3 B4s and 3 Gs. Reeks of simulation. Obviously, this was not done through some random process. California horn snail, B2. Cantharus, B4. Seraph, B2. Chinese cone snail, B2. Clamshell, SG. Cockle, G. Common Janthena, G. Cone snail, close-up. I wanted to do a close-up to show you how precisely this matches up with the geometry of the cone snail. And look at these. This is also a close-up to just ask the general question. I know if I had measured many of these angles, these GRS angles would have shown up here. This has to be computer generated by something. Conus glorimaris, B2 and B4. We see the B2 again in the bottom and the B4, but there's also a triangular object that's in the aesthetics here, which has a B4 geometry. And again, we could measure all of these smaller angles if we did a close-up, and we'd find that these angles show up there as well. Coquina clams, G. Earshell clam, B3. Eastern melampus, G. Episcopal miter, B2.5. Fighting conch, B2 and G. Florida cone, B3.5 in this case, and G. Florida nutmeg, B4. Helmet shell, here's an interesting one. This angle is a Giza geometry, and then we kind of move out from there to the next stage, and in this stage, we find the B3 geometry. Horse clam, S4. Imperial cone, B3. Lacinato conch, B3. Lampshell, G. Lettered olive, G. Jingle, B7. Junonia, B2 and B3.5. Limpets, B7. Marlinspike, B1.5. Marsh periwinkle, B4 and S4. Mitrini, I'm sure I didn't say that right, apologize, B2.5. Mud snail, B3 and G. Murex, B3. Mussel, G. Nautiloids, B1. And the nautilus shell itself has the leading edge of the Giza geometry. Nuculana, B2 and B4. Who knew that these shells had all this sacred geometry in them? And here's one of my very favorites, the nudibranch. This is actually a shellless mollusk, but when you look at the tips of its tendrils, fingers, you're going to find the B2 geometry. Oyster, S2. Parwelk, G and S4. Periwinkle, G and B7. Pimpled basket, B3. Pinna, B3 and S4. Princely cone, B2 and B2.5. Dwarf or purple dwarf olive, B4. Rib top, G. Rosy wolf snail, B3. Scallop, SG. Scotch bonnet, SG. Shark's eye snail, G and SG. Now, I've marked this as an anomaly because this is the way supplements, would look in the real world. They would be inline, or at least in theory, inline supplements. And this is the only example that I could find where an angle and its supplement showed up in line together. So I just wanted to mark that as an anomaly. Sharp angled cone, B3 and G. Shellhorn, B3. Slug, a slug is the only mollusk, another mollusk without a shell, but I'm just showing you here that it has antenna with the G geometry, as does this snail. A squid has B4, G, and B8 geometries in its anatomy. And here's one of my favorites, the star snail, B3, B4, and G. You can't tell me this is an accident, because it's not. These are all driven by algorithm. Sundial snail, SG. Sunray Venus clam, B2 and SG. Terebra, B1.5. Terebralia palustris, B2. Trigonia, B3. Tresus, S4. Top shell, G. Triton's trumpet, B3. Tulip snail, B3. Turban snail, G. Turkey wing, B3 and B6. Turritella communis, B1. Unionidae, G. Volute, B3 and B4. Wintelwrap, B2. Whelk, B1. Wormshell, B1. And that's going to end our section on mollusks. But as you saw, each and every mollusk that we found had used these geometries. So the mystery of how are the geometric angles that make up the seashells and the mollusks has now been discovered and reverse engineered. Echinoderms are other sea creatures, starfish, brittle stars, sea urchins, sand dollars, and sea cucumbers. And sure enough, we find the same angles there as well, B2, B3, S4, G, and B7. This is called the brittle star, and it has the Giza geometry. Here's a sand dollar. We see the B2 geometry there. C biscuit, we see the G geometry. These look just like the flower petals that we explored in the plant section. C cucumber, S4 and Giza. C urchin, S4, starfish, B3 and B7. Now we're going to move on to fish. This is really one of my very favorite sections as well. Fish incorporate golden ratio scaling into their fins, the front portion of their bodies, the rear portion of their bodies. We're going to find it everywhere. Now, the fastest fish, the ones who swim the fastest, tend to use the B2 geometry in the front and the rear of their anatomies, as well as in their tail fins, whereas other fish species use a number of differing GRS angles. But before we go any further, I want to just point out the fact that this same B2 geometry is going to be found in the nose cones of our commercial aircraft. So pay attention to the hydrodynamics of these B2 fish. I'll point them out as we go along in our discussion. African climbing perch, G and SG. American knifefish, G in the front and B2 in the tail. Angel sharkfish, look at this, B1 scaling geometry for the gross anatomy and Giza geometry in the front. I could have measured these fins as well. They all have them. But I'm just showing the basics. Bala shark, B2 and B4. Barberfish, we see the Giza in the front. We see the B3 geometry in the tail fin, and we see B3 being used for aesthetic purposes to define the space or the intersection of the white and the black components of the skin, the scales. Barracuda, B2 and B4. This is one of the faster fish. So once again, you're going to see that B2 geometry in the front. Barrier reef anemone. I wanted to show you this because you can see even from the front that the geometry for aesthetics of the color separation uses GRS angles to make that separation. The black sea bass has the B4 geometry in the snout, and also the B3 geometry is defining the geometry of its eyelid. Here's a close-up of the black-striped surgeonfish mouth. And I wanted to do these when the photographs were of good enough quality. I could really blow them up and still get precision. I wanted to do that to show you how precisely these geometric angles fit. So the outside, the snout geometry is using the SG geometry, and then we see there in the mouth itself the B6 geometry reflective of roughly a 90-degree angle. Black tetra, G, blue chromis, B4 and G, blue spotted jack, G and SG. We'll see the G in the front and the rear, and then the SG in the fin. Blue face angelfish, again a close-up, SG geometry. Blue striped snapper, B4 in the front and the rear. Blue tang surgeonfish, B2 and SG. Blue throat wrasse, got the SG in the mouth section, and the fin has the G geometry. Boccasio, B4 front and rear in the tail fin. Bonito, B3 and SG in the fin. Brassy chub, B4 and G. Brown banded bamboo shark, we've got B4 in the snout. And also we have an aesthetic of Giza there with the stripes. Humphead cichlid, we've got G in the snout. Look at that close-up, how perfectly these match. Here we have the clarion angelfish, which has the SG geometry in the snout and uses the B4 geometry to define the geometry of the eyelid. Here we have the clown triggerfish with the G geometry in the front and the S4 geometry in the tail fin. Copper rockfish, B4. Copper band butterfly fish, SG, both in the front and in the tail fin. Coral grouper, B4. Crab, SG. Crevice rockfish, G. Cuttlefish, S2 and G. Here we have the damselfish with the B3 geometry in the tail fin and the B4 in front. The Indian tang, we've got G and SG. We'll see the SG is being used in the front. The G is used both in the rear tail fin, as well as in defining the change in color on the rear of the fish on the side. And then we see the SG again being used to define the difference in the angles of the lines showing up on the fish. So we have two aesthetic examples here and two perhaps more functional, potentially examples as well. Dolphins, B2 and B3. Earth-eating cichlid, B4 and G. Electrical eel, B2. English sole, B4. Look at how perfect those are. I mean, it's just perfect matches. Eye-striped surgeonfish. We've got B4 in the tail fin. We have the B3 geometry defining the side fin, and then we have the S4 in the front of the fish. Fish scales as well. There's many of these, but so I'm not going to do a lot of these, but fish scales also grow with these very same geometric angles. And we'll see another example here. Here's a different species with the B2 and the S 3.5, something we don't see very often. Flag rockfish, B4 and G. Flame angelfish, what a great close-up of this G geometry. Perfect match. Flameback yellowfish, B4 and G. Four-eye butterfly fish, B4 in the front. Giza in the fin, and then the B8 at the back end of the tail fin. French grunt, B4. Galapagos shark, again, one of the fastest swimming fish in the ocean. Got the B2 geometry in the front and the G geometry in the tail fin. Garibaldi, B4 and G. Giant manta ray, B2 and SG. Golden trout, B4. Gold-spotted spinefoot rabbitfish, G and SG. Great barracuda, again, B2 and B4, one of the fastest fish in the ocean. Great white shark, B2, fastest fish in the ocean. Greenland shark, now it has a B3 geometry, so it's obviously not as fast as the others. Green crab, G. Green sea turtle, B2. Harlequin tuskfish, another good close-up, in this case with the B6 geometry defining the front of the fish. Horseshoe crab, B4. Horseshoe leather jacket fish, B4 and G. Humpback whale tail fin. I saw this, I had to measure it, and it is a perfect match. Hard to imagine, but perfect match. Japanese spider crab, B4. Coal tang, B3 and SG. Lesser electric ray, B1, defining the scaling of the tail, and B4 in the front. Lions Cove yellow labido, G. Lobster, B2. Long ear sunfish, SG. Long fin pennant fish, G and SG. Long nose hawkfish, B1 and B2. Again, if these are angles in fluid dynamics that are associated with high-speed aircraft. Long snout boarfish, B2 and B8. Lyre tail fairy basslet, B4 and G. Magpie perch, B4. Mako shark, again, one of the fastest creatures, B2. Manatee, G. Marlin, B2, again, fastest fish, B2 in the front and the rear of the fish. Mobula ray, S4. Moonlighter, G in front and SG in the fin. Here we see the octopus with the SG geometry. More importantly, I looked at the octopus sucker and I said, I bet you if I could find a diagram, I would find these angles in those suckers. And sure enough, I found a diagram. It's over on the left, and we can actually see the SG geometry at the base and the B3 at the top of the sucker. So golden ratio scaling, even in the suckers on the octopus. Old wife, B4. One spot rabbitfish, B4 and G. Here's the orca whale with the B4 geometry. Ornate cowfish, B4 and G in the tail fin. Pacific spadefish, SG, again a close-up of the face. Pallet surgeonfish, SG. Panamic fanged blenny has a G geometry. Panther grouper, B4 and G. Penguin, B2. See the aerodynamics of the hydrodynamics of the penguin in both the front and the rear using the B2 geometry. Pelagic stingray, SG and B8. Pharaoh cuttlefish, SG. Pink whip ray stingray, SG and S4. Pompano, G and SG in the fin. Popeye catola, G and SG. Purple queen anthias, G. Rainbow surf perch, B4 and G. Red-bellied piranha, G. Port and starboard lightfish, S4 and G. Red-breasted wrasse, B4 and G. Red rainbow fish, B4 in front and rear. Red Sea mimic blenny, B2 in the rear and B4 in the front. The red-tailed triggerfish, SG. Rock wrasse, B4 and B2. Royal Gramma basslet, B4, front and tail fin. Here's a sailfin tangfish. Using, again, the SG in front, we see the tail fin has the B2 geometry and the color separators on the side of the fish use the Giza geometry to make that color separation. So purely aesthetic uses once again. Sailfish, B2 in the front, and we'll see the tail fin of the sailfish is the SG geometry. Sally Lightfoot crab, G. Sapphire devilfish, B4. Sargo, B4. Scissor tail sergeant major, B4 in the tail and SG in the front. Scribbled angelfish, G in the tail fin and SG in the front. Scythe mark butterfly fish, SG. Sea butterfly, B2 and B3. Seven-striped cardinal fish, B4 and G. Silky shark, another fast swimmer, B2 in the front and rear. Silver arowana has the Giza geometry. Slipper lobster, B2 in its gross morphology. Southern stingray, G and SG. Spotted ray, B4 and SG. Spotted gill cardinalfish, B3 and G. Spotted unicorn fish, SG. Square-tailed grouper, this is one of my favorites. because it has so many angles. B1, B3, B4, G, and SG all in one fish. So we see the B1 up here in the top left-hand corner. That little fin there is being scaled with the B1. The tail fin with the Giza. The middle fin here is the B4 geometry. SG is in front, and the B3 is down here on the bottom, which defines the separation between the blue and the yellow or gold colors on the fish. So, this is a classic example of GRS angles staring you right in the face now that you know what they are. Squid, B4, G and SG. Sunburst anthias, G and SG. Swallowtail damselfish, B2 and G. Swordfish, again, fast swimming fish, B2, front and rear. Thread fin butterfly fish, we see B4 and Giza in the front and in the tail fin, and then we see the Giza being used for the stripes on the fish. Tiger freshwater stingray, G. Treefish, B4 and G. Trout, this is the fish that Victor Schauberger used to figure out nature. He found these golden ratio scalings in this trout. So this is such a great example, but this is where Victor Schauberger ostensibly learned about the secrets of nature and golden ratio scaling. Truncate butterfly fish, B4 and SG. Tuna, B4 and B2. Two-band anemone, G. Vanderbilt's chromis, SG. Wahoo, B1 and B2, again, fast swimming fish. Weedy scorpion fish, very hard to actually make the anatomy out because it's such a good camouflage, but it's the SG geometry. Western blue groper, B2 and G. Whale shark, B2 and SG. Again, a fast swimming fish with the B2 in the snout. White-tailed damselfish, SG and S8. Wild discus, G and SG. Yellow long-nosed butterfly fish, B2 and G. And yellowfish tuna, B2 and B4. Yellowtail kingfish, again, B2 and B4. And this ends our section on fish. The next section we're going to talk about, we're going to move into butterflies and moths. This next section is going to cover butterflies and moths, and there's some of the really great examples again of golden ratio scaling geometries. You're going to see these same basic geometric angles in the wings of the butterflies and moths. So let's get started. With the angles you're going to see: S1, B2, B3, B4. Giza, SG, B6, B7, and B8. So we're seeing a few of the somewhat unusual, but are less used geometries. Here's the American copper butterfly with the B2 down at the bottom, the tail end of the butterfly, and the S1 geometry delineating the two upper from lower wings. American snout butterfly, B4, both in the antennas and also in the wings. Aphrodite fritillary butterfly, B4, G, and SG. Notice as well here that one of the B4 geometries is for the pyramidal shape decorations on the wings. So another case here of finding the GRS angles being used for aesthetic purposes. Black swallowtail butterfly, B3 and S4. Caterpillar, the front of the caterpillar has the SG geometry. Crocopia moth, B2, B8, and Giza. Clearwing moth, B3 and S3. SG, excuse me. Comet moth, G and SG. Eastern blue-tailed butterfly. Again, we'll see the Giza geometry in the antennas and the SG geometry in the wings. Eastern tiger swallowtail butterfly. Beautiful butterfly. B2, S2, G, and SG. Again, you see the combinations of the base angle with the supplement, and it's done twice in the same butterfly. Elephant hawk moth, B2. We see that geometry 3 times in this moth. The emperor moth, we've got SG and the antennas, Giza separating the wings, and the B3 showing up here at on the backside of the moth. False tiger moth, B2 at the base and G at the top and on the wings. Gallium sphinx moth, B2, B4, and S6.25. So again, we're seeing the SG25 is in the antennas. Garden tiger moth, B1, S3.5, and B5. Giant leopard moth, B3 and B7. Gray buckeye moth, G and SG, with the Giza showing up in the antennas. Gray hair streak butterfly, we've got B4 for the antennas and B2 and S4 in the wings and the back of the body. Hackberry emperor butterfly, SG twice. Hercules moth, we've got B2 separating the 2 wings and the B4 on the edge of the wing. EO moth, we've got B4, which is separating the goldish or yellowish color from the more reddish color. We've got the Giza geometry separating the 2 major wing, and the B6 geometry on the edge of the wings, representing roughly the 90-degree angle. Japanese silk moth, B2.5, G, B6.25, and B8. So seeing a whole bunch of different angles here in the Japanese silk moth. Lime hawk moth, every angle that we measured here was a Giza geometry. Luna moth, we have a B3 in the antenna. We have a B4 in the wings, and then we have the SG defining the top wings. Madagascan sunset moth, B2, B4 in the wing, and Giza geometry separating the 2 front wings. Monarch butterfly, B3. Oleander hawk moth, B3 and B4. Orange sulfur butterfly, G and SG. Painted lady butterfly, G and S1. Polyphemus moth, B4. Queen butterfly, we'll see the B4 in the antennas. Then we see some of this, just like we saw in the leaf veins. We're going to see these in essentially the veins of the wings. We're going to see B3 and B4 as well. Red admiral butterfly, G for the antenna, and then we see the B4 in the wings. Rosy maple moth, got SG here along the front edge of the wings. We've got B2, and we have B4 in the wing. Rothschildia aurota moth, B2, B4, and B7. And once again, see the purely aesthetic geometric or triangular shapes here have the B2 geometry. Silkworm moth, B7. Spurgehawk moth, B3 and S5.5. Twin-spotted sphinx moth, G on the edge of the wings, S4 along the edge of the wings, and B8 on the far side of the wings. Two-tailed swallowtail butterfly, G. Viceroy butterfly, SG and B3. Weidemeyer's butterfly, G and SG. White line sphinx moth, B2, G, and B 6.25. Once again, we're seeing that 95-degree angle show up. Not at all a surprise, given the fact that this is a simulation. And the wood nymph butterfly, we see B4 and the antenna and B3 in the wings. Zebra swallowtail butterfly, B2 and B7. We're going to move on to turtles and tortoises. They provide some of the best examples of golden ratio scaling used for purely aesthetic purposes. And there are many examples of pyramidal shapes containing all of these angles. We've seen most of these before, B123, S3. We've got some B3.5s, S3.5s, B4, S4. You see, this is running the whole gamut. B5, Giza, SG, B6.25, 7, 8, and S8. So all of these angles are showing up in various places. What's interesting is to look first at the scales. Tortoise scales are a lot different than turtle scales, but you can see that they grow outwardly, again, using the Giza geometry, almost like a leaf would grow on a tree. Turtle scales, however, are a lot different. You can see that they don't jut out, but they form a kind of a pattern, a mosaic pattern, on the skin of the turtle. And we see these basic angles, the SG and the S4 geometries, showing up in the turtle scales as well. Now we'll start to look at some of the turtle shells themselves. This is an African box turtle. We're seeing the same old angles, B625, B7, B8. I don't see any way that all of this could have, even on this turtle, could have happened by accident. This is clearly some kind of an algorithm, and it's using these golden ratio scaling angles. African spurred tortoise, S3.5 and SG, that defines the apex angles of these pyramids found on these tortoises. Now, here's an interesting one. This is the bottom side of what's called the Alabama red-bellied cooter. But I happened to see this, and I had to measure it because I saw it automatically. And sure enough, here in the back, we find on the underside in these colorings, B4, S4, and SG. Again, nothing more than an aesthetic anomaly here. Now we'll start to see some of these pyramidal shapes showing up in the turtle shells themselves. Alligator snapping turtle, B1, B2, and B4. Here's an angulate tortoise. It has a number of these pyramidal shapes on its top of the shell. But we can see here we've got B3 angles separating these, and we have the B2 geometry in the triangular shape at the base of the tortoise. Now here is another view of the same angulate tortoise shell, but what I've done is I've measured this angle, and we found the B4 geometry in that particular position as well. Asian forest turtle, SG and B8. Bollinger's Cape tortoise, B8. Here's a desert tortoise. Again, we see the same angles. Got an SG and an S4 going on in this example. The East African black mud turtle, I found this picture and found some interesting situations, somewhat unique. You see the B3 geometry at the very bottom there. That's sort of how the shell comes together on the underside. Then we see the SG geometry up here, and then we see the B6 in the face of the turtle, in the jaw. Eastern box turtle, we've got two B4 geometries and one B2. Probably could have measured more, but you're going to see a lot more as we continue on. Here's a typical turtle face. We're going to see the Giza geometry and the stripes. We're going to see the SG geometry in the top of its mouth, and then we'll see the S4 geometry in essentially the jaw of the turtle. Here's a false map turtle. Again, the underside. You see that, interesting pattern on the bottom, but if we look at these depressions, we've got the G and SG geometries, and we have another SG here on the edge of the turtle. Galapagos tortoise, S3.5 in the shell. Geometric tortoise, look at this. We'll start from left to right, B3, B2, B3, 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 Giza, and B3. This can't be anything but an algorithm. Giant river turtle, S4. Green sea turtle. This is the underside of the green sea turtle. B4 and G geometries. These geometries are everywhere. All right, here's a hinge-back tortoise, S3.5 and S4. Indian star tortoise, all Giza geometries, 76.345. Another Indian star tortoise. Look at all of these tortoise shells. You can't tell me that this wasn't done on a computer. But anyway, this is another tortoise shell with geometries of B2, B3, and we've got two B2s and three B2s and two B3s on this tortoise shell. Another Indian star tortoise, B1, B2, B3, and S3. Another Indian star tortoise shell shape. We've got a B1 and we've got three B3 geometries. Here's another Indian star tortoise shell, and we see the G and the SG geometries in these geometric shapes. Here's a leatherback sea turtle. We've got B6 in the main body, and then on the head, we've got the SG geometry. Leopard tortoise, B1, B2, B2.5, and G. This can't be an accident. Loggerhead sea turtle, SG, S4, and B7. The musk turtle, we see the G geometry, Giza, in the face of the turtle, and we also see the SG in the in the turtle shell. Ouachita map turtle, we see S2.5 and S3.5. Here's a pancake tortoise with the S2 geometry in the shell. Here's another radiated tortoise, B4, B2, B3.5, and Giza. Here's another radiated tortoise, B2, SG, B7, B8, and S4. So clear, so precise, so accurate. This can't be anything more than an algorithm. Another radiated tortoise, B3, SG, B7, and S4. Russian tortoise, S4. Serrated tortoise, S4, Giza, and B3. Serrated tortoise, B3, B4, Giza, and SG. Snapping turtle, S4 in the shell. Tent tortoise, 3 SGs, pyramid shapes. Tent tortoise, look at all these angles again, B1, B4, and Giza. Terrapin, interesting, look at the eye. We're going to see more of this later, the B3 and the geometry of the eye. We're going to see this in mammals and human eyes as well. So we also see the S4 and the B7 geometry in the face of the terrapin. Western box turtle, got a B4 geometry here in the pyramidal shapes and the SG in the face of the turtle. Western pond turtle, S2. And the final is yellow-footed tortoise, which is an S4 geometry. So that ends our turtles and tortoise section. We're going to move on now and look at reptiles. See the same geometries, B2, S2, B3, S3, B4, S4, G, and B8. So here's a front end of the alligator. You see the S4 and SG geometries in the alligator. Here's some examples of snake scales. And I did a close-up of the boom slang snake. And we see here that we've got the B3 and the SG angles being used in the snake scales. Now here's another one of the anomalies showing up. This is purely aesthetics, but the boa constrictor triangular shapes all have the Giza geometry. The chameleon's face has the B4 and the G geometry. Crocodile, G and SG. And you see the G is twice, both in the chin and here between the eyes. Many other angles we could have measured there as well. Another major anomaly here, diamondback rattlesnake scales, Giza geometry. Here's an eastern diamondback rattlesnake with both the G and the SG geometries. Gila monster, B4 and B8 in the mouth. Here's a green vine snake. This is one of these classics. It just couldn't fit more perfectly. We see the B4 geometry here on the side of the mouth, and we see the Giza geometry here at the top. Hognose snake, we've got a B8 angle showing up in the scales, and in the snout, we see perfect match with the Giza geometry in this close-up. King cobra, B2. Komodo dragon, S4. Python scales use the G and SG once again for defining their scales. This is a triangular shape atop the eye of the thorny devil, which has the Giza geometry, and in the back we see we see the B2 geometry. Now we're going to move on to rodents. Rodents are mammals characterized by a single pair of continuously growing incisors in each of the upper and lower jaws. About 40% of all mammal species are rodents. So same old angles, S1, S2, S2 and a half. These are somewhat unusual. We're going to see those in the head of the rodents. But the traditional angles, B3, B4, S4, 5.5, G, SG, B8, they show up as well. So here's an example. We can see these incisors that we were referring to here in the beaver. This is a great underside view. You can see that the geometry of the beaver, the front of the beaver has the B4 geometry. Now you're going to start to see this is the first example of what we're going to be seeing a ton of with felines, canids and canines, and mammals and primates as well. But what you're seeing here is a B4 geometry that precisely defines the angle of the ears on the chinchilla. You're going to see the Giza geometry, and then you're going to see B8 and S2 as well. So we're going to see a lot more of that, but let's get into some of these specifics of, for example, the chipmunk. You're going to see the Giza geometry around the snout and the face, but you're going to see an S2.5 geometry defining the angle of the head. So these S2s and S2.5s, this is a gerbil. The gerbil has the S2 geometry at the same position. Here's a gopher. We see the Giza again in the front. We see and two other angles, the S1 and the S2.5 here in the head as well. Groundhog, we see the Giza geometry separating colors, as well as the B8 geometry in the mouth. Guinea pig, again, we see S2 and B8, the S2 in the head area and the B8 in the snout. Hamster, again, S2 showing up in the back and SG in the face. Porcupine, we see the B4 and S4 geometries in the face. A rat, slightly different geometries, but they all seem to fit together nicely for unique situations. The ear has a B3 geometry. We see the S2 again on top of the head, and a unique angle, the B5.5, is in the snout. Now we're going to move on to amphibians. Amphibians also use these same angles, B.5, B2, B3, 4, S4, Giza, SG, and B8. These are just the same angles we keep seeing all the time. African bullfrog, SG. American bullfrog, look at this, how interesting this is. We have both the B2 and the B3 geometry showing up in the side view of the bullfrog. This is an endangered species called the axolotl, but it's quite a unique looking animal, but it has these scaling angles as well. Got the B.5, the Giza geometry, and the B8. Barred tiger salamander, we see these interesting splotches here, but I wanted to show you that even in things that may look random, the algorithm is behind this because we're seeing the B3 geometry here, and the SG geometry right here. So even when it looks confusing, the algorithm is hiding things either through imperfection or other means to keep this from being quite as obvious. But we've detected them, and we have 3 examples here in the barred tiger salamander. Cane toad, S4 and G. Crucifix toad, S4 and SG. Long-nosed horned frog, B8 and B4. Red-eyed frog. Now, this is the first example we're going to have. I'm going to start measuring eyelids throughout the balance of the presentation. And this is the red-eyed frog that has an SG geometry in its eyelid. Moving on now to birds, this is going to be a tremendous opportunity, again, to see these angles in birds. Due to their need for aerodynamic bodies, birds use golden ratio scaling for their wings, tail, and beak. Whenever used for these purposes, the B2 angle is generally the exclusive one found, but birds also extensively use GRS angles for aesthetic purposes. So we're going to get into all of that. Here's the albatross. We're going to see this B2 geometry in the base. This will look exactly like the tail of a commercial airplane when we get to that, because the geometries are exactly the same. Bird's beak. This is important. I'm going to show this a couple of times, but the beak of the bird has the B2 geometry every time. Now, here's some examples from a chicken. You can see the geometry of B4 seems to be present in the gross morphology of this chicken. But just to confirm that that's not just a supposition, we see that a chicken drumstick has the B3 geometry. The chicken heart demonstrates the B3 geometry, and the chicken wishbone demonstrates the B4 geometry. So, that's all I'm going to do with these. We're going to see a lot of these in humans, but I wanted to show you that these exist in all types of animal situations as well. They're using these all the time. Okay, moving on, we'll see the crane here. The beak of the crane is the B1 geometry, and the separation between the white and red fur is accomplished with the Giza geometry. Here's a beautiful picture of a dove. You're going to see this beak has a B2 geometry, and the wing is a perfect B4. Eastern screech owl, again, another example purely for aesthetics. You see that the eyebrows, as well as the separation of colors and so forth are both accomplished in a sense. In this case, it's sort of like the mustache of the around the bird's mouth. Both use the SG geometry, but this is all aesthetics. Emu, we see the S2 just as we saw on the heads of the rodents in the back. Flamingo beak, B2. Another anomaly here, we can see it more clearly here. We see how the white fur is delineated in one case by the Giza geometry and in the other case by the SG. Here's one of my favorite pictures, the golden eagle. We could see the B2 in the beak. We've got a B4 geometry at the bottom of the mouth, a B3 in the on the side of the mouth, and here again we're seeing these eyes. I'm measuring the slant of the eyes, and that appears to be a B3 geometry as well. Great gray owl, again, we're seeing this aesthetically just to separate colors. We've got the Giza geometry accomplishing that function. Great horned owl, same thing, B2, S2 in the B2 in the beak, and then S2 and SG in the top and in the eyebrows. Heron, we're looking at the wing. We can see that the wing is, uses the B4 geometry. A hummingbird, perfect B2 in the back, just like we saw at the beginning of this section. And equally as important was this B2 geometry found in the hummingbird's wing. So we'll be seeing that as well in fluid dynamics. Ibis is a B2 and G. Kegu, I hope that's right, has the Giza geometry. Kiwi, B4. Long-eared owl, again, aesthetics only, Giza and SG. The loon, we see B2 in the beak, and we also see B2 in this little kind of, aesthetic necklace or neck piece that we see on the loon. The mandarin duck has the B2 geometry in the beak, and it has the B4 geometry in the white portion of the feathers on the back of the head. This is called a masked booby, S2, B4, and B8. Here's an ostrich with two S4 geometries in its face. And here's a peacock. This is a picture I took at a local caverns that had some peacocks. I happened to see this when we were getting ready for the tour. This is the backside of the peacock, but I had not really been aware before because I'd never seen the backside of a peacock that they had these other sets of feathers that conformed to the Giza geometry. Now, the peacock has other examples of this as well. If we look at the geometry of the plume, it's B4. And certain species of peacocks have these designs on their feathers where we see both the Giza geometry in the veining and also the B3 geometry in this dark blotch of color. The peregrine is the fastest bird, flying bird on planet Earth. It has the B7, the B8, and the SG geometries. And it also incorporates, as we saw before, the B2 geometry is prominent in its tail end as it begins its dive bombing. And it's when it's diving that it's the fastest bird in the world. Now, this is a pigeon feather. Nothing more than pure aesthetics here. We see these markings, another example of the algorithm being used purely for aesthetic purposes. Here's another one of these great anomalies. I was looking through rooster combs and I happened to see this one. And I said, oh my God, did these all match up? And sure enough, they do. They're not terribly precise, as you can imagine, but you can see that the B2, B3, B4, G, and SG geometries show up in this rooster comb. And it seems to be species specific, because here's another rooster comb that has only B2s, but it has B2s. every single time. So it certainly looks to me as though, this is all just for show and it's all done by the algorithm. Here's some beautiful rooster feathers that have the B1.5 geometric angle. Here's the wing of the scarlet macaw, perfect B2 geometric angle. Here's some more geometric angles, the S4 showing up in the wings of the scarlet macaw. And this is called the southern cassowary feather. Now, what's unique about this particular feather, this bird is the only bird that has a bifurcated feather. And you can see it comes to a point here at the bottom, but those two bifurcations use the B1 geometry for bifurcation. Another example of the southern white-faced owl where we're seeing these angles, SG and B7, used for aesthetic purposes. And the spectacled owl with the S4 and SG geometries as well. Here's a stork with the B1 geometry in the beak. The sun bittern with the Giza geometry in its feathers. Here's a swift. You can see the B1 in the back portion of its anatomy. We see the B2 in the wings, and we see the B8 geometry in front. This is the tinamous, B4 in the rear, and Giza or G in the front of the body. There's a toucan. We'll see, these are the kinds of things that you don't realize if you don't know what you're looking for, but we've got a B1 geometry in the orange or reddish orange color, and then in the lime green, we've got the B2 geometry. Turaco, B4, and its little, peak of its hair. The western grebe, S4. And now we're going to look at some anomalies of webbed feet. Sure enough, webbed feet come in three sizes. B3 for flamingo. Ducks have B4, and geese have Giza. So all of these things that you always thought were random, they're not random at all. All right, here's a wild turkey. We'll see the B4 geometry is essentially defining the vertical geometry of the wild turkey's breast or body shape. And then we have B4 and B8 geometries. The B4 is showing up in these feathers at the top of the plume, and then the B8 geometry is down below. So woodpecker, B1 in the beak and B4 in the top of the head. And that concludes our study of birds. Our next section is mammals. The world of mammals is also filled with these golden ratio scaling angles, and it's the same list: B1, S1, B2, S2, S2.5, B3, B4, S4, G, and SG. So here's an American black bear. It's 2.5 geometry. It's what's delineating the lighter colored fur from the rest of the face of the black bear. Armadillo, we'll see this B2 geometry in the contour of its face as well. I took some examples of our armadillo scales and put them in here. We see the same geometric angles all the time. We see S4, SG, and B7. A bison, the head has the S4 geometry. A cottontail rabbit. This is an amazing photo because what it shows is, again, this progression. We've got the B2 geometry at the base of the ears. Then we move to the Giza geometry, and then we move at the top to the SG geometry. So there's another example of this concept of progression that we see in the rabbit ears. Here's an elephant's ear. We see that they are angled with the SG geometry. And here's an example of that upper ear angle, and that is an S4 geometry. An elephant's trunk is scaled in the B.5 geometry. And now I've got two examples of horses, and we'll see some variation here, but this is really, I didn't do a whole section on horses, but here's an equine head. We see the B4 geometry in the ears. Here we have the Giza geometry separating the darker fur from the white fur, and we have the SG geometry forming the angle of the head. Now here's another head from a horse, and we're going to see slightly different angles. We're going to see at the top of the head, we're going to see the B4, and then down here, we're going to see a B2 geometry. Gemsbach is a B2 geometry in the face. Here's a giraffe. Look at all of these angles here. We got B4 in the ears. We've got B4s in these humps on the top of the giraffe head. We've got B4 here, scaling up the face, and then we have Giza defining the geometry of the head. Here's a grizzly bear. We see the Giza geometry defining, its lower facial features. Here's a hedgehog with the B4 and the Giza geometries. Here's a hyena. We see the Giza defining, again, the top of the head, the SG geometries defining the ears, and the bottom of the mouth. Here's a kangaroo. We've got the Giza geometry defining the geometry of the ears, and the B4 showing up between the eyes and the nose. Here's a koala bear with the B4 geometry defining the sides of the head, and our favorite from the beginning, the panda bear. If you've ever wondered what makes them so cute, well, a big part of it is the B4 geometry defining the black spots on the face of the panda bear around its eyes. Here's a pangolin. This is an species that's close to extinction. It has scales that grow with the SG geometry, and its face has the B2 geometry. Here's a polar bear, B2 geometry and SG going up and defining the geometry of the bear's ears, and the B2 defining the angle of the head. Rabbit face, we see B3 in the ears, and here I measured the eyes again. We've got the B2 geometry showing up in the eyes. See all of these different angles in the raccoon face. Again, we're using SG and B4 to define these angles, just like in the koala bear. That's geometries defining these black hair spaces. And we see the Giza geometry defining the nose. Red panda, again, Giza defining the shape of the skull. We've got a B4 in the ear geometry, and again, Giza defining the separation between the white and other colors on the face of the red panda. Sea lion, we see it in two places. In the gross morphology, we see the B2 geometry, and then we see the B3 geometry in its flipper. Here's a sheep with the B4 defining the color of the fur on the face, and also a S2 geometry defining the skull. Here's a shrew with the B2 in the front and the S2, getting familiar with that, on the top of the body. Here's a sloth with the Giza geometry and the S4 geometry. The spectacled bear, actually, again, we see the use of the SG geometry to delineate changes in fur or skin color on the bear around its eyes. The tapeti rabbit, SG geometry, both in the angle of the ears and also in the geometry of the mouth. Vampire bat, I love this one. We see two examples, the B4 geometry in the ears and the B4 geometry defining the bottom of the mouth. Here's a wallaby with B4, G, and SG geometries. Here's a warthog with the SG geometry, and a zebra. We'll see the Giza geometries in the ears. We see the B3 geometry in the fur in the middle of the zebra's head between the two ears. The zebra also has some anomalies. It's a classic way of demonstrating that this algorithm, for aesthetic purposes, just shows up everywhere. Because here we're taking a picture, an example of the zebra stripes. That's a B3. And then we go out one more level and we've got the Giza. So these are being defined by this algorithm as well. Here's an S4 geometry defining the verticality of the stripes, and an a B8 geometry defining the outline of the head. And finally, another anomaly of the SG, it's what in many zebras defines this change in the stripes that shows up on the back of the zebra in many of the species. So another hidden example of these geometries. So now we're going to move on to felines, and felines represent another great example. We're going to be looking primarily at facial features with felines and some of these other higher level animals because that's the easiest place for you to see them, just as we saw before. So once again, we'll see the Asian lion. We've got B4 and the Giza geometry defining the skull. Bobcat, the ears are G, and we see the nose is defined, the bottom part of the nose is a G, and then we see two SG geometries for aesthetic purposes. The Canada lynx, look at these little tufts of hair, and they are perfect match for the Giza geometry. We've got the SG defining the skull, and we've got Giza and SG down here once again, the lower part of the nose and the jaw. Caracal, B4, S4, and SG. And here's a picture of cat fur. I found this just to see what it would look like under a microscope. And sure enough, each piece of fur, just like almost like a palm tree, has little growths on it. And when you measure those growths, you find the B3 geometry. Cat's mouth, when you get the right angle, you see that it's angled at the perfect B4 geometry. Here's a clouded leopard with the G and S4 geometries. Here's a colo. This is a pretty interesting photo. I mean, let's look. We've got Giza at the bottom. We've got Giza at the top. We have B3 here on the ear, and we have B8 here at the top of the mouth. And here's a domestic short hair. We have one that looks very much like this cat, and we see how perfectly the Giza geometry defines the angle of the cat's ears. We see that the eyelid or the eyes are slanted with the B2 geometry, and the chin area is defined with B7. Here's an exotic short hair, B4 and B8. Iberian lynx, B4, G, and SG. Jaguar, B4, G, and SG. Leopard, G, SG, and S4. But you see, all of these angles are always using these same angles. Here's a lion. Here's a lycoi. This is one of my favorites. Every one of these angles is a Giza angle. And we could have measured the slant of the eye. Probably that wouldn't have been Giza, but it would have probably been B3, I think. Lynx, B4, and Giza. Margay, B4, G, and SG. Here's a very close-up shot of the ocelot, G and B7. Here's what's called the ossicat, G and SG. It's a cross between a cat and an ocelot. And again, just look at how perfectly these geometric angles show up in the faces. And on Scylla, G, SG, and B7. And this is another one of my very favorites, the Oriental Shorthair. We've got the SG geometry defining the angle of the ears. We've got the Giza geometry, or G geometry, defining the shape of the head. We've got the B2 geometry defining the slant of the eyes, and the G geometry defining the base of the nose. Here's a puma, G, SG, and B8. Ragdoll, B3, G, and SG. Selkirk Rex, B4, SG, and B7. A Serval, B2, and Giza. Look at all of those different Giza geometries showing up in that face. Snow leopard, G, B4, and S4. Sunda-clouded leopard, B4, G, and SG. Tiger, G, SG, and B8. And a tiger eye. I did a close-up on this. I still have some issues to be, I'm always going to be as honest here as I can. I like this close-up. I don't have a way to reference absolute horizontal using, my methodology. So I blew this picture up and drew my line across as kind of a surrogate so you could at least eyeball it over the distance. It looks to be pretty close to pure horizontal. So it looks as though this angle is the B2 geometry in the slant of the eye. White Bengal tiger, G, SG, and S4. So now we're going to move on to canids and canines, and they use the same basic angles as primates and felines. And once again, with the Giza and SG angles being the predominant ones. But we'll see B1, B2, B3, B4, S4, G, SG, and B7. African wolf, B3 and B4. I called it an anomaly because this little bow tie here is nothing but pure aesthetics, and it's being done with the B3 geometry. Alaskan Klee Kai, G and SG. Alaskan sled dog, B4 and G. Arctic fox, all Giza angles. Black timber wolf, G, SG, and B8. Boxer, G, SG, and B8. And look here, I've measured the eyelid of the boxer, and it has that Giza angle. Bulldog, look at all these angles. B3, B4, S4, and B7 in the face area of the bulldog. There's a bull terrier, just like the rodents we were looking at. It's got the S2 geometry showing up at the top of the head. We'll see the S4 geometry back here at the interface with the ears, and then we'll see the Giza geometry. Again, aesthetics separating essentially the dark from the light fur. Here's a chow chow, G and SG. This is more subtle, but they're still there. The coyote has a B4 ear, an SG top of the head, and it defines the colors on the underside of the eyes, as well as the geometry of the white fur at the base of its jaw. There's a dhole, B2, B4, G, and SG. Doberman, B1. Dogmouth, just like we did with the cats, B4. Ethiopian wolf, B2, G, and SG. German shepherd, B2, B4, and G. Golden jackal, B4 and G. Golden retriever, now we're measuring the slit in the eyes here, and that's a Giza. Then we've got the ear with the Giza geometry and the face, and then we see the S4 in the bones in the head. Gray wolf, G, SG, and S4. Greyhound, B2 in the torso. Japanese chin, B3 and SG. Pekingese, G and S4. Pomeranian, G and SG. Pug, B3, G and SG. Red fox, B3 and SG. St. Bernard, SG and B3. And look at this Weimaraner. I can't, this is great. I mean, the Giza geometry shows up even in the way that the dog's ears appear in 2D as they flop down. It's just amazing. Wolf, B2, B3, and SG. Now we'll move on to our next section, which is horns and antlers. Another one of these classics, because every horn and every antler on every animal shows up as one of these angles, B2, S2, S3, B4, G, or SG. Here's the addax. This is a unique set of horns because it actually, again, shows progression. We start with the Giza geometry right next to the head of the animal, and then after that, we see the B4 geometry. Arabian oryx, B1. Look at all of these angles. The antelope, we have two Gizas, and we have an SG as well. This is called the Ankole longhorn cow, B1. Here, the 145.68. Excuse me, that's the S2.5, and the B1 is 13.557. Barral has the Giza geometry and its horns. Bighorn sheep, we see on the bottom area, it's a B4 geometry, and then it converts to a Giza geometry at the top. So we see both the B4 and the G in the bighorn. This is a skeleton, or skeleton of, or skull of a bison, I should say, and you can see the B4 geometry in the curvature of the horns, and then the scaling angle of the horns is a B1. Deer, this is just a generic deer, but we'll see the S4.5, that's a unique one in the deer. The eland has the SG. Elk has SG. A fallow deer has two geometric angles. The B3 defines these front horns, and the B8 defines the angle of the larger horn complex. Gemsbok has a B3 geometry. Goats have B2. Golden oryx, B2. Ibex, B4. Kudu, B4, and Giza. Longhorn, S3, and Giza. The Manx Lawton has the Giza geometry. The Markhor, B4 geometry. The moose, S2 and SG. The mouflon has both S4 and SG geometries. And what's interesting to note here is that in the first and the first one on top here, we're measuring that angle in the vertical plane, and we're measuring it in a different plane from the overhead view, essentially the Y plane, I guess. And so we're seeing these angles show up no matter which orientation or perspective we take to make these measurements, which is pretty profound in and of itself as well. Pronghorn, G geometry. Reindeer, B2, B3, and SG. Scimitar horned oryx, B2. Sitatunga, G and SG. Springbok, B3. Thompson's gazelle, B2. Water buffalo, B6.25. And again, remember, that's that 95-degree angle, so it seems to be important to the person doing the simulation to have access to that 95-degree angle. Now it's time to start getting a little bit closer to home. We're going to start talking about primate faces here. And then the final section in the animal kingdom will be demonstrating GRS angles in the human body. But primate faces, along with those of the other animals we see, rely exclusively on these GRS angles to define their facial features as well as provide beauty, to each of the animals. So again, the angles we're going to see, B2, S2, B4, S4, G, SG, the same old culprits, and the B7. Now, there's a lot of these, and I think what I'm going to do is after I introduce a few of these, I'm going to go silent and let you listen to some music. But here's the Abbott's Gray Gibbon with the G and S2 geometry, and I'll let you go from there. Now that we've seen the comparisons in the primate faces, it's time to move on. Our final section in the plant and animal kingdom is going to be looking at human organs and body parts. And although they're clearly not as visible as we find in less complex organisms, human organs and body parts all contain one or more of these GRS angles. And we'll see those. Once again, it's the same list: B2, B, S4, G, and SG. So let's get started. We're going to see the B4 geometry here in the geometry of the lower ear. We're going to see the B4 geometry, and I picked two different eyes just to demonstrate that it works no matter whose eyes you're looking at. If they're wide open, they're going to demonstrate the B4 geometry. This is a human hair, and I attempted to scale that from this microscopic photograph, and we get the B.25 angle. The base of the heart has the Giza geometry. Large intestine has the B2 geometry. And the lips have four of these angles. On the side here, we see the B3 geometry. And you can see kind of how the lip transitions here, but all the way through, like right there, that B3 geometry is spot on. And then we look over here on the other side, we have the Giza and SG geometries showing up here, and then we have the B8 geometry on the top of the lip. So yeah, geometry apparently has something to do with beauty. So I'm sure that after this is done, that people in the fields of perception are going to have a field day once they understand this information, because this is going to unlock so much information about how we perceive things and what may be beautiful or not beautiful. And that may, in fact, just be a function of the algorithm. Liver, B4. Lungs, G. Nose, look at these perfect matches, G. Pancreas, B4. Plantar fascia, B3. Here's a cross-section of a male testicle, and we see the B1 geometry there. The thyroid, B4 and S4. The tongue, B4, S4, and G. The uterus is roughly shaped in the B2 geometry. Here we have some vein branching. This is just a diagram. It's tough to get anything more than diagrams on these sorts of things. But I found a B2 geometry and the Giza geometry in this diagram of human vein branching. Now here's another diagram of an arm vein branching, and it has the B3 geometry, and that looks to be very, very precise. Now we're going to look at human skeletal and muscular system. We have numerous bones and muscles in the body that use these GRS angles. We found one as thin as B.25, but the main ones are B2, B4, S4, G, and SG. So we'll look at these. Muscles in the body are an amazing way to see these angles. As you can see, we've got the G geometry here in the back of the shoulder. We've got B3 as well. So we've got these angles in a couple of different places in the back. Here's another back shoulder muscle. This was a close-up I saw on Bing Images. I measured it, and it was a B4.5. Now, the breastbone in the human body scales, that piece at the bottom of your breastbone has the B2 geometry. Here is a diagram of chest muscles I found, which shows the B1.5 here in the left-hand corner. We've got the B2 geometry going on here in the chest, and then we have the B1.5 geometry. We saw this kind of cut in the stria of the muscles. So I measured that as well. So we find it in the chest muscles. This is a diagram of the human coccyx, and we see that it contains the B4 geometry. Face muscles, again, we're going to see the Giza geometry here at the top, and also in these muscles underneath the lip, we're going to see a B1 geometry right here. We've got a B3 showing up here. So we've got facial muscles with plenty of these angles showing up. Now here's the floating ribs. They appear to be angled at the Giza geometric angle. Here's the gluteus maximus. You can see the Giza geometry down at the bottom. And then, interestingly enough, the SG geometry reflects the angle of the two glutes, on each side of the top of the leg. Here's some hand muscles. We see the SG geometry showing up, as well as the S4 geometry. Here's a picture of the human jaw with the S4 geometry forming the outline of the jaw going up into the head. Here are two geometric angles from the pelvis. We saw these in the introduction. We have the S4 and the SG geometries in the pelvis. The phalanges have the B2 geometry. The rib cage here, we're going to see at the very tip that this is a very precise measurement of the B4 geometry. Can't be an accident. And as we move up the rib cage and do another measurement at the top, we find the Giza geometry. Shoulder blades, we'll see the base of the shoulder blades have the B4 geometry. And then we're seeing this in the vertebra, the B7 geometric angle. Here's a perfect example of showing a shoulder blade and some shoulder muscles. We see that Giza geometry there in the shoulder. And here's another example of shoulder muscles, and we've got the B2 geometry showing up there as well. Looking from the back and measuring, it looks as though the angle of the human skull is scaled with the GRS angle of B2. And also the spine appears to be scaled with the 0.25 geometry. And here's a diagram of stomach muscles. We'll see the B8 geometry, the S1, and the SG over on the side. And here's another measure of same picture measured, another set of muscle stria that have the SG geometry. Now we'll move on to human teeth. The roots and the teeth faces all have these angles as well. So we look at the a human canine tooth, we see the Giza geometry on the top of the tooth, and in the root, we see the B2 geometry. This is an incisor called a mandibular incisor, has the B1 geometry in the root. Here's a molar, has the B2 in the root and the SG geometry in the faces on the top of the tooth. Here's just some animal teeth. I saw a picture of that. They're no different. They have the same angles. Here's a SG, here's a B4, and here's a B2. So they seem to be virtually identical. Now I want to show you, because this, I think, in terms of future research, could be really, really important. There's not a lot other than diagrams that you can find. I did find a micrograph of DNA, but the sensory receptors, all you can really find are diagrams because it's hard to photograph them. But when we look at all of these receptors, we're going to find that these angles show up once again in our DNA and our sensory receptors. So here we have human DNA. This is an electron micrograph photo of human DNA, and it has the B4 geometry. Now we're going to look at cones. The rods I couldn't find pictures of, but the eye cones have the B1 geometry. This diagram, at least, and it's very hard to find anything but diagrams that you can measure, but the cochlea has the B4 geometry demonstrating. Olfactory receptor has the B2 geometry, as does the taste receptor and touch receptors. So, along with the SG geometry and some of the branching. So, and this is the last slide for the animal kingdom. This is a picture I found of dendrite branching. Now, dendrites are part of our neuron system, and they act as information receivers for neurons. And this is important because we're going to see again these very same angles in telecommunications down the road. But you can see that I've been able to identify three major angles on this one photograph. We've got two B2s, we've got two B4s, and we've got an SG geometric angle showing up in the neuron. And these neurons, again, receive information on behalf of the neurons. So that is the end of our section on the animal kingdom. I want to summarize it for you very briefly. You know, the insect and small animal world is a live classroom of golden ratio scaling. The gross morphology, the antennas of these animals all use these golden ratio scaling angles extensively. As you just saw, numerous human organs and bones incorporate GRS angles. These angles are found for purely aesthetic purposes everywhere. Turtles, butterflies, zebras, you name it. We've got aesthetics showing up with these very angles all throughout nature. And although larger, more complex animals do not demonstrate these angles as openly or easily to see as insects and small animals, one area where they can be seen easily, as we saw, is in the facial features of larger animals, including humans. We just saw that the gross morphology of the human sensory receptors and DNA all contain GRS angles. And I want to make this point in summary. This information is totally new to the world of biology. I was a biology major. I've done tons of research. I have not found anything close to what I have just demonstrated in the plant and animal kingdom, namely that there is a fundamental process, in this case growth, that is quantized in nature. So this is a major new discovery. And what this, I hope, will entail is the beginning of a new science in biology of non-locality. We've already proven, as we talked about at the beginning, that we don't live, local reality isn't real. It's been disproven. We live in non-local reality. This is the first comprehensive demonstration that biology is affected by non-locality. So I'm hoping if any of you out there are working in an academic or research context and would love to get this started, I am looking forward to working with academics and other scientists to get this started. I would love to see this become a subfield of biology, because once people see that it works in biology, they're going to start to realize that it's going to work in all of the other subject matters that we're going to be talking about in the balance of this presentation. Now that we've finished discussing the plant and animal kingdom, I think all of you will agree that we have definitely found an algorithm that seems to be involved in every aspect of growth in the plant and animal kingdom. So it's very, very challenging, especially with the demonstrations of all these aesthetic angles and the other anomalies and so forth, that this is truly an algorithm that we've found. And this is the first scaling algorithm of growth that we've found that's universal within the plant and animal kingdom, to my knowledge. But with that information as background, I now want to start to get us into some of those other a dozen or so areas where we find these very same angles. But before we start, I just want to kind of talk about the significance of what we've just found and how it impacts the information that we're going to be seeing going forward. I've done a lot of research, as I mentioned earlier, into architectural sacred geometry and also in fluid dynamics. So I've seen this in other places. And I have to say, even though I've done a tremendous amount of work on those when I would try to explain this to people, say in mechanical engineering. Most of them, to be quite honest, would think I was goofy. And I can understand why, because there's no context in which they could appreciate this information. But going forward, I hope that now that we've seen this in nature, so-called, it's actually the simulation, but we've called it nature. I have for a long, long time. But the simulation is controlling these aspects of the organizing principles in the universe. We're going to find it in others as well. So hopefully now that we've seen all these in nature, that's all I'm saying, it's going to be easier because there won't be as much cognitive dissonance to the left-brainers like me out there who had a real tough time coping with this before I saw this in nature. So we're going to start with some natural phenomenon. And I didn't want to go over that. There's only a few of them that we're going to talk about, but I want to open up now and show those to you and show you how one of these angles shows up in each and every one of these phenomena. So here are the four natural phenomena that we're going to talk about briefly. They all use the B2 geometry. We're not going to get into that in this documentary, but I'm working with other researchers who have made some amazing discoveries, and we'll be talking about that. But again, this documentary is primarily based on showing how these angles show up in all these different areas. So the four natural phenomena we're going to look at are light refraction, sound amplification, tornado funnels, and water vortexes. So this is a diagram from a research study that was done by an individual who took a pipe. You see that black section there? That signifies a pipe. And he put a glass sphere at the end of the pipe. What he next did was to position the pipe such that direct sunlight would come streaming through onto the sphere. And the reason why he wanted sunlight as opposed to an artificial source is because he wanted as close as possible to get an infinite distance, so there was no discussion of refraction of the light until it hit the sphere. So this is essentially a straight line of light coming in from the sun. And what we find is that the B2 geometry shows up in the refraction of light through a sphere. So what this demonstrates to me, I was kind of guided to originally use, as I showed at the beginning, those stacked circles and spheres. That concept is right on the mark here because we're seeing that light will refract through a spherical subject at precisely this B2 geometry. So I think that's going to be significant, particularly in the context of research that we are now doing and will be doing on these specific geometries going forward. Same thing holds for sound amplification. We're going to see three examples of this here. These were called, I believe, ear trumpets, maybe, but this is an early form of hearing aid. And they use this B2 geometry to amplify sound. I think there was some electronics here that maybe amplified that, but I'm not sure, but it uses the B2 geometry. We see that also in the logo of the old RCA Victor company. This was one of the, RCA was one of the early giants in televisions and radios. And you can see here the Victrola, the company, which they bought, and it became RCA Victor. That Victrola used this B2 geometry to amplify sound as well. Then here on the right, we see that the classic old college football megaphone has this very geometry as well. So we've seen light refracts at this geometry, and sound is amplified with this very same geometry. Tornadoes have in their funnels this very same geometry as well. Just for a brief explanation, not every tornado funnel that you're going to see a picture of is going to have this geometry, and that's largely due to the fact that tornadoes go through a building phase and a degradation phase. And it's only when they are mature that you're going to see at their peak of energy that you're going to see this B2 geometry. We'll see the same thing in water vortexes. If you've ever seen spinning water vortexes before, you'll know that they can have different geometries sometimes. But when they're at full speed, just like the tornado, those vortexes will end up with this B2 geometry, um, you know, being demonstrated. So there's not a lot more to say about this except to discuss it now in the context of simulation. All of this isn't real. This is nothing more than a simulation. So doesn't it make sense that these fundamental phenomena would use the very same geometric angles that we see in the algorithm to produce these phenomena? So I don't think it's unreasonable at all. Now that I have had several months to digest the kind of the gestalt of what we just saw in the plant and animal kingdom, this makes perfect sense to me. Now we're going to go on to musical instruments. Musical instruments of all types use the very same GRS angles found in the algorithm, although the angles are generally steeper than those found in nature, but they're still within the algorithm. So we're going to see a different kind of subset, but it's the same algorithm. All conical bore instruments, that's brass instruments, I used to play the trumpet, and saxophones are all what are called conical bore. All those conical bores, and we'll see those, use one of these angles in the bore of the pipe. We're going to see this in organ pipes and so forth as well. And then we're going to see that all the percussion instruments, including, interestingly enough, all of the indigenous drums from around the world, use one of these angles. So that is another, question. I was led to look at all these percussion instruments, and I measured every one of them, and they all show up. So we're going to start with conical bore wind instruments. And again, that's things like trumpets and saxophones and so forth. And we're going to see these angles, as I said, they start at the low end and they don't go up that high. But we've got B.125, B.25, B.5, B.1, and B2. So we're going to start, again, maybe a bit speculative because of the potential imprecision, but this is the Alphorn. And this is a conical bore instrument. I'm sure all of you have heard those Ricola commercials. Well, that's what this is. It's this Alphorn. And I tried my best. This is a shot. But given the fact that everything else matches, I'm not going to say that this doesn't work just because, my precision, is wanting a little bit on these steeper angles. But that appears from top to bottom to be a B.125 angle. Trumpet, which I used to play. This is the conical bore section of the trumpet. All of the other sections prior to this, in the trumpet, are not conical bore, and that bore starts at just about where my cursor is right here. That's where the conical bore starts, and it ends just about here. And these are the two locations where the conical bore piece is melded both to the bell part of the trumpet on the left side and to the main body of the trumpet on the right. But it has the B.25 geometry. I also measured the bore in a trumpet mouthpiece. And sure enough, we get the exact same B.25 bore going into the mouthpiece of the trumpet. And I got a very long angle here, very good shot, and they all seem to match up. So it seems as though, the precision is not an issue here, and it looks like it's exactly right. And then if we look roughly at the depth of the angle of bore of the depth of the mouthpiece, that is the B2 geometry. Now moving on to other brass instruments, we've gone from the B.125 to B.25 in the trumpet. Now, from here on out, we're going to see B.5 bores in the French horn and the larger instruments. French horn is probably the hardest because there's such a small section of straight pipe that's, using this conical bore. But I tried to do that the best I could, and it looks as though that B5 geometry is accurate. And when I look at a baritone, much easier to measure. The B.5 shows up. shows up in the tuba as well. And again, you can see here on the tuba, there's a little plate there. That's where those two pieces of tubing come together in this particular version of a conical bore instrument. And, the cone or the, horn section here at the end, bell section, is going to start somewhere in this area, but it's a B.5 as well. Now, here's an example of a saxophone. And again, I measured from basically the top down to the place where the next piece shows up, but that conical bore section is B.5. Now, as I said, I used to play the trumpet. I just decided to pick up a straight trumpet mute picture and see what it looked like. And sure enough, it's just spot on with the B1 geometry. Here's some mouthpieces for woodwind instruments. We're going to see the clarinet and the saxophone both have the B2 geometry in the mouthpiece. And then over here on the right-hand side, these are reed instruments, as they're called. And the bassoon reed, which is essentially the equivalent of the mouthpiece for a clarinet or a saxophone, has the B1 geometry, and the oboe reed has the B.5. So again, we're seeing it everywhere. Conical organ pipes, there's two types of pipes. There's conical, we can see the B1 geometry in those, and then they're called reed organ pipes. And sure enough, they have this B1 scaling geometry in their pipes as well. We'll look briefly now at indigenous drums and percussion instruments. And I looked at these from all over the world, and I was just shocked to find that all these instruments have these geometries. And now we've got to start asking ourselves in the context of a simulation, how could all of these indigenous cultures have known about these geometries? And is this information that was left to these cultures in some way in the simulation? Anyway, all speculative, but let's continue on and look at these angles in these drums and percussion instruments. This is called the agogo bell, comes from West Africa, has the B2 geometry. This is called the agung. This is a percussion instrument from the Philippines with the B4 geometry. Ashiko in West Africa, that's a B1.5 geometry. And this is atabaque from Brazil, B2 geometry. Bambula has the B2 geometry. This is a set of 3 drums called bata from Nigeria. And interesting, it has the B1.5, the B2, and the B3 geometry. At some point, I want to go check out and maybe start to take these geometries and convert them into harmonics, because I'm sure that these drums have very specific tones that they produce. This is the bonang in Java. It's from all over the world, B3 and SG. This is the boogaraboo from Africa, B2 geometry. This is called the candombe, I bet, from Uruguay, which is the B2 geometry. The conga drum from Cuba, B2. This is called the coltron. It's a popular drum in Chile and Argentina with the Giza geometry. This is called the damaru. It's popular in Buddhism and Hinduism, has the B4 geometry. The goblet drum from Egypt has the B4 geometry. The ganga bell from Brazil has the B1 geometry. This is the gudu drum from Nigeria, has the Giza geometry. Kabero from Ethiopia and Sudan has the B4. Kinong from Java, B2 and G. Klong Yao, this is from Thailand and Laos, has the B2 geometry. Kundu from New Guinea, B2. Mridangam from India, B1.5 geometry. The Nagara, this is also the area of India that has a pyramid, a temple geometry that we're going to be looking at later. But the Nagara drum from India, SG, Ingoma drum, the B2, Sambal from India, B4, Timbal from Brazil, B2, Tumba from Brazil, B2. And to finish up, I have many more examples of these, but I only put in some samples so that you can see this exists everywhere. So it brings up as many questions as it answers. How did these indigenous cultures find these sacred geometric angles, and how did they get them? Next section I want to talk about is everyday technology. This is just stuff that we see in our everyday life, and I measured them, and sure enough, they all have these angles. So that's why I wanted to show them to you. They're going to, when you look at them, you say, "Oh my God, I didn't realize, that these things were so prevalent." But we're going to see B.5, B2, B4, and G and SG. I forgot to put that on the list here for one of these, but we'll see those in everyday technology. One of those examples is racing boat sails. Uh, Virtually all racing boats, have sails that have this B2 geometry. It's very close. Usually when you get to the very top, it steepens up a bit, but for the main part of the sail, you've got precision there with the B2 geometry. Now, I'm going to say these aren't accidents. These people who build these boat sails and all this technology, I can guarantee you, knew nothing about golden ratio or golden ratio scaling when they designed these. But what it turns out to be is that these angles were used because through trial and error, they turned out to be the optimal for their given use. So in a boat sail, we're seeing a B2 geometry that's in the interaction, with the air and the sail. Here's a Dutch windmill. We see that same B2 angle showing up again in the angle of the windmill. We're going to see it in not ancient, but 19th century technology. This is an iron furnace. These iron furnaces existed throughout Pennsylvania, the Northeast, down, I believe, as far as Georgia. But wherever you could find coal, and you had the raw materials for making iron, you were going to find these iron furnaces. Well, the important thing here is that the slant angle of these furnaces uses the B2 geometry, and apparently that's done because it maximizes the heat flow, probably because it maximizes the flow of air through the furnace. Now, we're going to see that that's true in a contemporary context here, because that very same angle ended up being employed in natural draft power plant cooling towers. Now, these cooling towers are used all over the United States and the world, and it doesn't matter what country you're in, you're going to find this geometry in every one of these cooling towers. Now, the reason why that's important, again, this turned out to be the optimum angle to allow for the natural drafting, upward drafting of this steam from these power plants. What's going on in here? They're taking the hot water from either a coal or a nuclear plant, and they kind of disperse it through kind of like a sprinkler system inside this cooling tower, and that produces steam and it comes up. But in the absence of good geometry, they would have had to put like a mechanical fan at the top here to pull the steam out to make the thing work. But using sacred geometry and these angles, they have found that they can do this without need for a fan, which cuts down tremendously on operating costs. Now, again, why would this happen? Why would these angles show up, the precise angles that we found in nature, when the people designing these, they didn't have much of an idea, if any, that sacred geometry was involved. So they've just found these angles on their own and backed into them. So hopefully, as this information gets out more and more, people are going to start to say, well, maybe if there really is an algorithm that is working and we're seeing it demonstrated here, maybe we ought to work with the algorithm and try to conform our geometries and all of our technology to maximize their benefit by using sacred geometry. Here's another example, the Sibley tent stove. This was a Civil War stove that was used to uh, keep tents for the troops warm during the Civil War. And it has this B2 geometry as well, just like the power plant cooling tower. Here's some common day technology. You look at the water skis, the geometry of the front of the water skis is B2, and the scaling geometry on the rear of the water skis is a B.5. Similarly, cross-country skis, we see the B2 geometry in the tip of the ski. We look at a surfboard, we find B4 geometries at the front and rear. Isn't this amazing? And nobody knew about this, from a sacred geometry standpoint. Vintage wooden snow skis have the B4 geometry in the tip. Moving on to some other technologies, you look at the geometry of a floodlight, and the bulb is angled with the Giza geometry. Here's a flashlight reflector with the B3 geometry. So we saw the B2 before. This reflector is using the B3 geometry. Pipe reducers. These are, in this case, these are liquid pipes, or carrying liquids. And again, they're not going to know what these angles are, but they sure show up. We've got the B2 angle here. We've got a B4 here, and a Giza geometry here in these three pipe reducers. So that can't be an accident or a coincidence. It must mean that because this isn't local reality, we're using an algorithm to maximize flows in these examples, and that's done best, I guess, with the algorithm that I've discovered. Now, these are duct reducers, and these are for air, but we're seeing the same angle showing up, B2, B4, and in this case, in the third one, the SG geometry for minimizing disturbance and maximizing laminar flow. Funnels, just pick three funnels out of the list in Bing Images. This is a simple plastic funnel with the Giza geometry. These other two are Pyrex scientific funnels. The one on the left has the Giza geometry, and the one on the right, which is called a titration funnel, uses the B2 geometry. Here's an Erlenmeyer flask. This was designed by Emil Erlenmeyer in the 19th century. He was also one of the fathers of other sciences that he was to do with organic chemistry. He did a lot of work with double bonds. And the reason that's interesting is because that's a way of increasing the energy inside of a molecule is by doing double bonds. Well, he found that these flasks were the optimal geometry for performing his experiments. And sure enough, what do we find but the B2 geometry in the Erlenmeyer flask? Here's a lot of wood splitting equipment technology, all using, once again, the B2 geometry. We see spikes and anvils and all of these other types of wood splitting equipment with the B2 geometry. Here's some drill bits. Everyday stuff we're talking about here. And here's some drill bits with the B4 geometry. And here's another one on the right. This is a wood drill bit with the B2. I saw this sword and I was able to blow this angle up. You can see this is a tip of a sword, and it's of an ancient, medieval sword. And this has the B4 geometry. Here we're going to see three common things that we use every day: a screw, a nail, and a medical syringe. And the tips of each one of these, again, B2. So this is clearly an important angle, and we find it also in chimney flues. So just picking stuff out of the air here, but these all are just examples of everyday technology, that we see every day. And sacred geometry, and these GRS angles show up every time. The next section we're going to explore are the various free energy technologies that, if you go out and search that you can find from the 18th to 20th century. And one of the key things that, interestingly enough, once again, all of these free energy technologies do is they all incorporate one of these GRS angles. Now, we'll get into a little bit of this as we go through. I'm not suggesting that all of the inventors knew about golden ratio scaling. We know from earlier parts of the documentary that Victor Schauberger did. I haven't been able to prove that the others did. However, we've seen these very same angles that we're going to see in nature. We've now seen these B2 angle, this B2 angle in specifics in natural phenomenon like tornadoes, one of the most powerful, if not the most powerful wind events, certainly that can occur on planet Earth, other than maybe a hurricane. But localized, I think it is the most powerful. So, we and water vortexes. So there's clearly something going on here. And I know that hopefully once people in the mechanical engineering world and here the free energy world see that these all match up and that this is really all part of the simulation, maybe we're going to, the next step will be to get people to say, gee, maybe we ought to work with the math of the algorithm we live in and see how we can use it rather than denying its existence. So anyway, with that said, the B2 and the B4 angles are the ones that you're going to see most. However, there is research we're going to talk about at the end of this section that indicates that all GRS angles can act as the Russians called it passive torsion generators, or to translate that, free energy generators. So we're going to start back in 1739. There are a couple of pictures that are out on the internet, and these are all from Paris in the early 18th century. This is a drawing of illumination that was occurring in Paris in the early 18th century. And we can see in this picture, there's a pyramidal structure, no surprise, with the B2 geometry that seems to be lighting up this area and perhaps providing the electricity for all the lanterns and stuff that we see in this picture. So that's one example. In the end of the 18th century, we find this drawing of lighting on the Champs-Élysées. We see what could be the equivalent of an obelisk, and it may be an obelisk that's in the front, but then we see these two pyramidal structures in the back as well that seem to be involved in that process, and they too have the B2 geometry. Now, if we move forward into the 19th century, this is a photo from John Keeley. He was a 19th century free energy inventor. He worked with water and developed a lot of water machines for free energy. This one is still, it's in the museum in Philadelphia. And we can see these bulbs here. These were, I believe, were filled with water, but they all use, in this case, the B4 geometry. Moving into the 20th century, these are more recognizable names to many of you, but Nikola Tesla, of course, we're virtually all familiar with, and he developed some free-energy technology at Wardenclyffe Tower. Interestingly enough, this geometry matches the B2 geometry that we found elsewhere. So it may be that Tesla knew about this as well, just as Schauberger did, but he definitely incorporated this geometric angle into his Wardenclyffe Tower. Now, this is an example. You can go see this out on YouTube. This is called the Royal Palace in Phnom Penh, Cambodia. It was built, I believe, around in the 1860s. We see this pyramidal type structure in the center. This is actually a free energy generator, and you can go on and see the middle picture there. You can see how this facility is, I believe we would call this doing ion harvesting, but it's producing free energy to this day, and it currently works. And we see on the right-hand side that we have a coil with the B2 geometry that I'm sure is intimately involved in the whole process. Getting into more recent free energy programs, we saw, as I said, Victor Schauberger at the beginning of the documentary. He used his knowledge of golden ratio scaling to develop what's he called the Vortex Home Power Generator, which is 10 times over Unity, supposedly, when it was built. And as we can see, the imploder here in the middle of this on the right hand, that's the device that's under that canopy type of device that Schauberger's holding onto on the left photograph. But if you take that off and you look underneath the hood, what you have is a B2 spinning vortex that supposedly produced tremendous amounts of free energy. And then more recently, and this, of course, as I mentioned at the beginning, this is the reason I got into studying this information. This is the most recent example of free energy research, and that was done with the Russian free energy research over the last 30 years or so. So I want to read this so that those of you who are unfamiliar with Russian pyramids will know exactly what they found when they did their research with respect to free energy. Instrument readings indicated the presence of an ionized energy field 2,000 meters or about 6,200 feet high and 500 meters or 1,550 feet wide along the vertical axis of the pyramid. The column was constantly changing its height from about 800 meters to 2,000 meters. The radar reflecting ability of this formation was similar to the reflecting ability of an airplane. Further studies confirmed that a larger circle of this ionized energy surrounded the area above the pyramid in a 300-kilometer range, with the highest concentration being directly above the vertical axis of the pyramid. Electrical energy from the pyramid could be harnessed by a capacitor that was placed at the apex of the pyramid. The capacitor would spontaneously take on a charge. Furthermore, pieces of the capacitor assembly were seen to break away and rise into the air on the energetic column that the pyramid was producing. There's a lot to unpack here, but two important factors. One, we see that electric energy was produced or was captured through a capacitor, and that happened very rapidly and apparently was quite powerful because that took on such energy that flew up into the air. The second thing is the existence of an extreme ionization field. Now, why is that important? Well, there are a lot of ion harvesting technologies that are at work that have been perfected today. We will be seeing some of those older technologies in Tartarian energy. But the key factor here is that that geometry alone has created this ionization field. That means that it's going to impact the ability to ion harvest. And that's why ion harvesting technologies from the 19th century, and we'll see those here in a few minutes, use this very geometry because it increased the ionization. So, hopefully we can, get people, once they understand that that the reason why this all works is because potentially because we're living in a simulation, maybe we can get some people to understand this and to test it more fully, with the knowledge now that this is all part of simulation theory. Another factor that came into my research as I was originally studying the effects of Russian pyramids was the research of Anatoly Akimov on free energy. Now, this article is very short, and it's actually deals with the growth of micellar structures inside of certain types of fluids from the body, like bile. But what it demonstrates is that, and I'm going to have to translate a little bit of this from even the English translation, but the plane geometry of the physical vacuum, we would call that probably ether, is distorted or changed by means of macro bodies or large objects of a certain size and shape. And thus, spinner or torsion fields of considerable strength can be created. If the bodies have geometric dimensions with fulfillment of the golden section or golden ratio, then they can play the roles of concentrators of the spinor field or free energy generators. So the key thing, we'll talk about this a little bit more, but this research has not seen the light of day in America. What happened to these technologies? Well, let's go through them one by one, and we're going to unfortunately see a pattern here. John Keeley, his research was sent to the Theosophical Society for Safekeeping upon his death, and there were concerted efforts after he died to discredit his work. He had a shop in Philadelphia, and he did many demonstrations of his free energy devices during that time. But we've essentially lost his notes. They're not available to the public. Victor Schauberger, similar kind of facts and circumstances. Many of you know that he had to work for the Nazis, building free energy and anti-gravity technologies during World War II. Well, after World War II, he kind of got brought over to the U.S. under false pretenses, and unfortunately was forced to, under duress, to license his technologies to American business interests in order to get the visa, which had been revoked, or his passport had been taken from him when he came to the U.S., in order for him to return home to Austria. He died, coincidentally perhaps, or maybe not, about 5 days later upon his return to Austria. Nikola Tesla, upon his death, his research was seized at the direction of the U.S. government by John Trump, an MIT electrical engineer and uncle of current President Donald Trump. The Russian pyramid research was not allowed to be published in scientific journals in the West after the Soviet Union collapsed. And finally, the Anatoly Akimov article that we just discussed, I was unable to get access to this article in the United States, even though I was told initially from Interlibrary Loan that certain places had it, and then they said they lost it. So I ended up having to get this from a library in London as well. So I don't want to get conspiratorial here, but this is what has happened. These are just facts, and I see a pattern. I wish I didn't, but it looks as though this information is perhaps valuable to certain people and institutions, and they don't want this to get out. Electronics equipment is our next section to deal with. And again, I'm going to say this, we're going to see these very same angles, a couple of them showing up in electronics equipment. They're not going to understand that these are the same angles that we're finding in nature and everywhere else, but I want to demonstrate that. And hopefully this will also allow people in electrical and electronics engineering to understand that this may act, this deserves some further testing. But it's interesting when we look at the design of certain electronics pieces, like the cathode ray tube. The tube itself uses the B2 geometry. I don't know how it got there, if this was done through testing or if someone knew about these angles in the past and incorporated them into the ray tube. But we'll see Crookes tube, another ray tube, has the B1 geometry in it. These are diagrams, so I can only use diagrams because you can't see this. But when I look at X-ray machine scatter diagrams, this one has a B1 geometry. This is a dental X-ray tube that seems to have a scatter beam of B2. This is a proton therapy machine, again with the B1 scatter pattern. Um, Here is an example that's perhaps, certainly more relevant to telecommunications to some degree, and that's an old style bow tie TV antenna. When I was a kid, we had these kinds of things, and in fact, the outdoor antennas sometimes had these bow ties as well. But I don't think it's a coincidence that the B2 geometry is showing up in those bow tie TV antennas, given the fact that this is very, very likely a simulation. Next one is a radar gun. The radar gun that the police officer uses to catch you, and the radar detector that you use to find the police officer with the radar gun, both use the B2 geometry. We'll go now into some telecommunications equipment. Microwave communications networks and interstellar horn antennas used to establish background radiation in the universe. All of these things use these same GRS angles, and as do satellite communications, rely upon these to send and receive information. The primary angles, B2, B3, B4, and G, and we're going to see a B.5 example as well. So let's get started. I'm going to start with the J.C. Bose Horn Telescope. This telescope was designed by Indian scientist J.C. Bose. He lived in the late 19th and 20th century, early 20th centuries. Many people feel that if he had not been Indian but had been Caucasian, he would have most certainly won the Nobel Prize. He was talented, a polymath in so many different areas, but he developed this a telescope to investigate the properties of waves and materials in the short centimeter to millimeter wave part of the spectrum. And this particular horn telescope that he developed has the B2 geometry. This is a horn antenna that was, or still, I think it's still there in Homedale, New Jersey. This was designed by Bell Labs and was operated in the middle part of the 20th century to detect and monitor cosmic microwave background radiation. And sure enough, it uses this same B2 geometry. Andover, Maine Earth Station. This was another Bell Labs project. This was located in Maine and was the first direct relay satellite communications satellite. So this was used with the Telstar 1 satellite. So this gigantic system would pick up the radar relays from the Telstar satellite. This is another experimental device called the Little Bighorn, and it measured radio waves coming from the sky's strongest non-solar radio source, Cassiopeia A. And it has the B.5 geometry. And again, the sacred geometry was not involved. They didn't know this, to my knowledge. And so all of these were derived through trial and error. Wouldn't it make so much more sense to have this knowledge in fluid dynamics rather than to have to keep testing, via trial and error? Here are some examples of microwave antennas. This is somewhat older technology. You don't see these as much anymore. They probably have come up with maybe somewhat more effective, or at least smaller sized units of this, but we'll see the B2 geometry in all of these microwave antennas. There are types of horn antennas called pyramidal horn antennas, and this particular one seems to demonstrate the B3 geometry. This is called a sectoral horn antenna, and the difference is that the sectoral horn is quite narrow in one plane, but it has the B3 geometry. Here are what are called conical horn antennas that contain the B2 geometry. And here is an exponential horn. Um, as you can see, we're seeing this progression again, B2, B4, and Giza in the different phases of that horn. So it's fascinating that they've kind of arrived at essentially the same thing that I would have theoretically, but they've done it essentially through trial and error. The Yagi antenna has the B2 geometry. This is the feed horn from the Webb telescope that sends back signals from the new Webb telescope back to Earth. So this is the transmission system, and part of that system is a B2 horn antenna, feed horn. Here's an example of some older technology from NASA. This is the Ames U2 microwave radiometer. I believe this was used on the old U2 airplanes, that very high altitude that we'd use to spy on the Soviet Union back in the 50s. Here's another feed horn antenna from a satellite for a satellite dish. This is the NASA Cosmic Background Explorer. This was put out into space again to monitor cosmic microwave background radiation. This was up, I believe, in the 1980s and had the B4 geometry. Now we're going to get into fluid dynamics. This is a major section. This is a section that I spent better part of a year studying. And so I know it as well as just about any other part of this, other than perhaps the sections on pyramids themselves. But fluid dynamics is a subdiscipline of fluid mechanics and describes the flow of fluids, liquids, and gases. Uh, it has several subdisciplines, including aerodynamics, the study of air and other gases in motion, and hydrodynamics, study of water and other liquids in motion. All of these fluid dynamics examples, as you're going to see, are going to show up with or demonstrate these very, very same angles again. As I said at the outset, this information I knew about before I went into nature. And so essentially the guts of the algorithm that I set up, the base part side of it anyway, without the supplements, was really coming from this research. So the first section we're going to look at is bullets and ammunition. We all know a bullet's a very simple airborne object, but it's perhaps in its most simple form because the bullet itself doesn't need any wings or for lift or any internal propulsion system other than the shot that it gets from the gunpowder. So it represents a really nice pure aerodynamic example to study. And what do we find there? We find the B2 geometry in all bullets. Now, as we move into heavier munitions, mortars, grenades, and other types of ammunition, we'll begin to see other geometries, primarily B4, but with respect to bullets and ammunition, only B2 and B4 are found. So let's get started. Here are two examples of bullets from every day, that we use every day in private use, non-military. But here's a military bullet, and this bullet this is the Mauser 8mm bullet. Was used during World War I and World War II. It has the B2 geometry, as you see. This was the basis for all of the aerodynamics for the V2 rocket, which itself became kind of the template for post-World War II aerodynamics. Now, if we start looking at bigger shells, one of the, in contemporary warfare here, the 155mm shell, that's the one of many that the U.S. is running short of in its conflicts, but it has the B2 geometry as well. There's some larger shells, such as this old Soviet 400mm artillery shell, which has the B4 geometry. So just like in airplanes that we'll see here in a few minutes, the faster they go, generally the narrower or the tighter the nose cone, and therefore the smaller the base length. Show you some more. This is the Fab 9000. This is, I believe, the largest you know, mortar round that's in existence, and it uses the B2 geometries both in the front and in the rear. This is American. Mortar shells, you can see the B2 geometry. We saw that in the back end of the birds. We'll see it in the back end of the airplanes, but mortar shells have that in the rear. Here's a grenade. We'll see the B3 geometry very clearly in the top half, and we've got the B4 geometry down in the base. Now, where does all of this lead us in terms of theory? Well, in World War II, as I said, the Germans used that 8 millimeter bullet kind of as the basis for developing the geometry of the V2 rocket. And in fact, the nose cone was left unchanged. And kind of confirming that is some theoretical work that was done by Wolfgang Haack in 1941, and then later by William Sears in 47. Wonder how Sears got his name first, but I guess that goes, the winners get to make the history. But anyway, what we find here is that this body shape is the shape with the lowest theoretical wave drag in supersonic aerodynamic flow. And when we measure that angle, what shows up? Nothing but the B2 geometry, another one of these GRS angles. Looking back historically into arrowheads, we're going to find these same geometric angles depending on how far, and where we're looking. But in the left diagram, we're going to see some B3 and B4 geometries. In those arrowheads, we have a B2 geometry on the left. What we do know is that these geometric angles must have been known for at least 70,000 years, because we found some old, archaeologists have found some old arrowheads in caves that they have carbon dated to that age. So interestingly enough, whether we knew how we got there, these arrowheads demonstrate that this knowledge was around for 70,000 years or so. Now I'm going to stop here, and I'm going to start to mention things in kind of non-local reality terms from here on out, because the alternative theory that I hope some of you may be thinking about is, are all of these artifacts real if we live in a simulation? I don't know the answer, but I think we all have to start rethinking. Once we know that we're not in local reality anymore, it's very easy for this to all be part of the simulation. So just kind of keep that in mind. I'm not trying to be conspiratorial, but we all need to open our eyes and minds to the fact that the world that we've been living in isn't real. And we're now learning that. So we've got to start thinking that way as well. Boomerangs, 20,000 years old. Another example of aerodynamics. The B1 geometry shows up in the backside of the boomerang, and the boomerangs have been around for 20,000 years. So the same angle, same principles of aerodynamics, if our history and simulation are right, we've known about this for a long time. Here's another example. This is the New Kingdom Temple helicopter hieroglyph. This was found in Egypt, and it has the B1 geometry. Here's some an ancient Japanese cave painting from about 5000 BCE, and it has the B2 geometry again. Look how similar it looks to the Sears-Haack body. It probably would have been narrower like that theoretical body were it not for the need for wings and propulsion. Here's an artifact from Turkey. Obvious UFO artifact that has the B2 geometry. Here's an Incan artifact of a flying machine with the B2 geometry. Mayan artifact with the B2 geometry. Same thing here. We're moving into contemporary culture. This is the British Congreve rocket with the B2 geometry. It was used against the United States by England in the War of 1812. Moving into the beginning of the 20th century, I wanted to discuss the Vimonica Shastra briefly. This is a supposedly channeled book um, that was published in the early part of the 20th century, supposedly depicting some diagrams and information on ancient flying craft. Well, I don't know about the validity of the rest of the book, but I will tell you this, that three of the craft that are in there, two of them have the B4 geometry and one has the B2, and they all are a perfect match. So, much more to discover here. Now we're going to get into contemporary aerodynamics, and my apologies if that was a bit extraneous, but I think we need to know that these angles have been around forever, and we're just relearning them. So this is the V2 rocket that was produced in Nazi Germany. You'll see here in the nose cone and also in the tail fins in the diagrams on the right, the B2 geometry. We could do a lot about World War II aircraft and so forth, but I'm going to leave that and we're going to kind of go into contemporary because that's the prototype. That's where everything else came from. And we'll kind of follow up with spacecraft and so forth later. I want to show you now how this goes into hydrodynamics as well. So this is the missile submarine from Russia has the B2 and the B4 geometries. If you look down below, we're going to see the B2 in the back of the submarine, and we're going to see that B4 geometry in the front end of the submarine. And it's the same way all the time. This is the Los Angeles class attack submarine from the United States. And here we see the B2 geometry both in the front and the rear. And in this case, I've shown it from two different angles. One is a top view and one is a side view, showing that, these are purely, basically conical structures at the front and the rear of this submarine. This is an old torpedo from 1877. It's called the Brennan torpedo from the United Kingdom. And sure enough, it has the B2 geometry as well. We'll be seeing this in airplanes here fairly soon. This is the Poseidon nuclear-powered torpedo. We'll see the B4 geometry. I mentioned sometimes this is a heavier torpedo, so I'm sure that's the reason why we're seeing that B4 geometry instead of the B2. Here's a Torped 47 torpedo from Sweden with the B2 geometry in the tail end. I've measured every torpedo that's been manufactured for military use. So if anybody wants more, I've got them, but we're going to, continue on away from torpedoes. Going to look at other ships now. The Ticonderoga class cruiser in the United States, we'll see the B2 geometry in the front of the craft. Here's the Kirov class cruiser from Russia, again with the B2 geometry in the front of the ship. Here's a Chinese destroyer, the Type 052D, with the B2 geometry in the front. Here's the Legend class frigate from the United States, B2. And here, from a different angle and perspective, is the bow of a racing boat, and we see that B2 geometry in that plane as well. Now, here's a kayak, I love to go kayaking, and I remember I needed to check this, and sure enough, the B2 geometry shows up in the front of the kayak as well. Now, this is the world's fastest speedboat. And this is the Spirit of Australia. And we see a picture of it here. I found this blueprint that gave me a great side and top view of this craft. And I wanted to show that from the side view, that the front part of this uses the B1 geometry. And it's harder to see here, but the B4 geometry, this is essentially the front here. This hull is separated and doesn't come to a point, but the geometry of the front of that boat is also B4. Now we'll start to get into racing. We've known about these, even the dads who design soapbox racers for their kids. I didn't know if geometry was giving them the right geometry was cheating or not. But anyway, these two soapbox derby racers from years past have have the B2 geometry in the front. Here's the world's fastest sports car, the Devil 16. It goes 348 miles per hour. Again, we see B2 and B1. We'll see the B2 geometry here in the windshield, and then we see the B1 geometry on the downside or the backside of the car. Now, I've measured every sports car on the planet, and every single one of them, a real sports car, is going to have these exact geometric angles. So they seem to be the best combination of minimizing, disturbance, maximizing laminar flow, and also helping to keep the car firmly on the ground. Now we'll look at Indy racing cars. We're going to see these angles once again. Many Indy racing cars are going to have this geometry, as you see in this top photograph, diverting the air from the front of the car, and then we're going to see the B1 geometry showing up in the side views. Now, why don't we see B2s here? The reason is if you did a B2 geometry and had half of it facing up, with the other half going down, you would essentially cause flutter, and the car wouldn't be stable. So apparently what they decided to do is just cut the B2 in half to get the B1 geometry, and that's what they use to to maintain the stability of the car through turns. And this is the Thrust SSC. It has the B1 geometry. It holds the world land speed record, and again, the B1 geometry in the front of the craft. Moving on to other aerodynamic examples. This is two examples of high-speed rail. This is the SC Maglev from Japan. It currently, I think, still is the world record holder for speed. It uses the B1 geometry. And of course, as is the case, the Chinese are about ready to introduce the fastest in the world at 1,000 kilometers per hour. This is the Chinese maglev with the B2 geometry. So you see it in maglevs as well. Now we're going to move into lighter than air vehicles and ultimately into airplanes, hypersonics. But we're going to start with a couple of dirigibles. This was the Baldwin dirigible that was made in the United States. You see the Giza geometry showing up in both the front and the rear of the craft. This is a German lighter than air vehicle during the Nazi era, has the Giza geometry in the front and the B2 geometry in the tail. Just some other examples, a hang glider. I saw this and I measured it. It looks as though the angle of the wings relative to horizontal is also a B2 geometry in this hang glider. Now we're going to get into some transport planes. These again are the heavier, bulkier, slower planes, but this is a Lockheed C5M transport with the B4 geometry. You can see it is a virtually perfect match for the Lockheed Nosecone. This is a similar B4 geometry. This is the Ilyushin IL-212. It has the B4 in the front and the B2 in the rear. And moving on, now this is a private jet. This is the Bombardier Global 7500 from Canada. It has the B2 geometry both in the front and the rear. Now remember, this is exactly what we saw in the Sears-Haack model. All commercial aircraft have this as well. BrahMos, this is a world's fastest cruise missile, and it has the B2 geometry in the nose cone. Pershing 2 from the United States does exactly the same thing, B2 in the nose cone. Here's some Chinese missiles with B-2. Same thing with the THAAD missiles from the United States. Now here's a Bell Osprey helicopter, Bell Boeing, and this has the B-2 geometry in the front and rear as well. This is the world's fastest helicopter. So we're just seeing this everywhere. And now let's talk about the airfoil of the helicopter. You know, these are not the same airfoils as I'll be showing you in this diagram, but a traditional helicopter airfoil looks something like this. This is a cross section, and here we can see this B2 geometry showing up in the front. And earlier I showed you the B1 geometry and the trailing edge of that boomerang. And sure enough, here it is in the tail end of the airfoil, helicopter airfoil. Now we'll get to commercial aircraft. Boeing 777. You'll see it's so simple to see this in the rear of commercial airplanes, harder to see it in the front because you need that cockpit there, and they're not going to do away with the cockpit just to improve aerodynamics. So what you have to do to kind of visualize that is to find blueprints with a top view to demonstrate these angles. So I've done that. I've got the top view of this 777. We see the B2 geometry from the top view in the nose cone and also in the tail section. So it's there in these planes. Moving into faster airplanes now, we see the Concorde SST. For those of you who weren't around those days, the French and the British co-developed the Concorde, and it was the first and only truly successful supersonic transport to ever make it to commercial service. Many more today are under construction in various forms of design, but this was the original, and it has the B1 geometry. Now notice that B1 geometry, just like we've seen in plants and everything else, it narrows out. There's progression going on here, and in fact, it ends up, into a nose cone, kind of a pointed end to the nose cone. But so we've seen Giza, B4, B2, and B1. Now let's see these in some rockets and some other situations. Now remember that our space program was handled by the group of German scientists who came over under Wernher von Braun. So I would assume most of these were done, by these ex-Nazi scientists. But this is the geometry of the nose cone of the Jupiter PGM-19, B2 geometry. This is what's called an experimental lifting vehicle, and it has no engine, so it has no method of propulsion, but this is purely a testing vehicle that tests geometries inherent in the craft to assist in lift of the aircraft. So sure enough, we look down here and we see the B2 geometry in the nose cone. We're going to see the B1 geometry in the tail section, and we've got the SG geometry on the underside. So I can't tell you if they knew this or if they just were able to deduce this from wind testing. But all of these angles show up. This is the WRE-SAT satellite from Australia. This was done, I believe, as a joint venture with the United States, and you can see perfect B2 geometry. Here's the contemporary Boeing Starliner. This is the craft that, unfortunately for the astronauts, couldn't bring them back home, but at least they got the geometry right with the Boeing Starliner containing the B4 geometry. Now, the SpaceX Dragon that went to pick them up, well, it has the B4 as well. The Sputnik 3 capsule, this was back in the 1950s. You can see it contains the B2 geometry as well. So you can see here finally the last section, the Sputnik 3 capsule from the Soviet Union. This was used in the 1950s, has the B2 geometry. Now, the next section we want to cover is hypersonic vehicles. Um, we've been hearing a lot about hypersonic. Some of you may know a lot about them, some of you may not. But a hypersonic speed is one that exceeds 5 times the speed of sound. And that's just an arbitrary point to call something hypersonic. Anything that's supersonic is above Mach 1. So hypersonic is now a newer term to describe speeds above Mach 5. Now, the race to build hypersonic vehicles and weapons you know, has accelerated due to the current geopolitical crises around the world. And, you know, for better, for worse, these factors have resulted in the successful development of hypersonic weapons by Russia, China, India, Iran, and North Korea. And in fact, maybe even by Pakistan. I don't know, but I don't believe so. But anyway, there's a name that's missing from this list, as you know, and that's the United States. And so we'll talk about that at the end of the section. All successful hypersonic development projects have used the B.5, B1, or B2 geometries in their nose cones. The United States, however, has chosen a different path if the information that's available out on the internet is accurate. And they've chosen to use a non-GRS geometry in its nose cones. Now, our hypersonic vehicles have not fared well and have disintegrated, when they've been tested. And I'm going to show you that I think it has a lot to do with geometry. I want to show you first, though, that all nations have known about these geometries historically, whether they knew them from this perspective of sacred geometry or whether they had been able to back into them through wind tunnel studies and experimentation. I can't really tell, but I will show you that everybody knew them. So this is a Boeing X-51 Wave Rider. I believe it achieved Mach 5.1 speed done by the US, and you can see the B2 geometry built into that craft. Now, this is the Hwasong 8, which is a North Korean missile, which goes Mach 5 plus. So they have that. I forgot to put them on the list. They're there as well, and it has the B1 geometry in its nose cone. Now, this is the Circon hypersonic missile, Mach 9, and it was built by Russia, and it also has this B1 geometry. Now, some people might wonder how these geometries got to all of these different countries. I don't know, but I will know that and state with certainty that Russia has been at the forefront of all of this for years. And in fact, at least some people in Russia knew about these geometric angles because they put them into their pyramids. But this is the Oresnik hypersonic missile. It got its debut in the Ukrainian war. There's nothing that we have to stop it. And it can go Mach 10 to 12, and it has the B2 geometry. This is the Kinzhal hypersonic from Russia, Mach 10, again, the B2. This is called the DRDO from India, and it appears that it has a B.5 geometry in its nose cone. This is the YFZF hypersonic glide vehicle from China, Mach 10, with the B2 geometry. We're moving up in speed here, if you hadn't noticed. This is the Fatah 2 from Iran, Mach 15 to 20. It has the B.5 geometry. Here's the U.S. Space Shuttle. This was the last craft, I believe, that Wernher von Braun worked on. And it has the B2 geometry, and I think it's significant. It was able to withstand reentry speeds of Mach 23 to Mach 25. So we knew that this nose cone worked with that geometric angle, for these high speeds. And now the fastest vehicle, at least according to current available data, is the Avangard hypersonic glide vehicle, again from Russia, Mach 27 with the B2 geometry. So again, we're seeing these very same angles showing up in these hypersonic and aerodynamic examples. And it happens every time except for one. And that one time, this anomaly is the HTV-2 missile of the USA, and it's non-GRS. To give you some background, in 2011, DARPA, which is one of our defense agencies in the U.S., it conducted a test of its unmanned hypersonic glide vehicle, dubbed Hypersonic Technology Vehicle 2, or HTV-2. The vehicle was able to maintain stable flight for a while at 13,000 miles per hour over the Pacific Ocean. The stable flight lasted 3 minutes before HPV-2's flight safety system plunged it into the ocean. The agency now thinks that unexpectedly large pieces of the hypersonic aircraft skin peeled off. DARPA says that it expected some of the skin to wear down due to the extreme heat and speed of the aircraft. An independent review board has concluded that the most likely cause of failure was the unexpected aeroshell degradation. Now, I don't want to go into too much, physics here or aerodynamics, but I want to explain something that's really important for people who aren't familiar with this. Drag, which is, the forces of pushing against you as you go faster and faster. Well, drag increases as the square of the velocity. So let me do a simple math thing. We know that Avantgarde went 27, Mach 27. I'll do the math for Mach 25 because it's easier in my head. But if we look at an object that's flying at Mach 1, well, a commercial aircraft is probably flying at about 3/4 of Mach 1, but let's just call it Mach 1 for math. The difference in drag between a commercial airliner flying at Mach 1 and a hypersonic at Mach 25 is 25 squared, or 625 times as much. So if you're going to have problems with you, it's going to show up when you're going that fast. So with that said, I'm going to show you the blueprint that is available on the internet. I can't promise that it's legitimate, but you can see here at the bottom, this is the same HTV-2 that was tested. And when we look at what I'm calling the vertical plane angle of attack to the atmosphere, this is very, very close to the 6.767, which represents B 0.5 geometry. So this could in fact be very accurate, but on the horizontal plane, we totally missed it. If you want to believe what I've shown you so far, it should either be 27.309 or it would go to 41.478, maybe with a B3 geometry. Never saw that but theoretically it could work, but we're not close to those. We're kind of in the middle at 33.4 degrees. So we've used these angles, whether we knew it or not in the past, but we didn't use it in this case. So if this is accurate, I would suggest that maybe we try one of these angles because everybody else uses them. And now we know that we're in an algorithm, which indicates we're in a simulation. So why don't we work with it rather than working against it? Finally, rocket engine exhaust nozzles. This is kind of an ancillary piece to fluid dynamics, but it's kind of in its own separate world. Rocket engine nozzle is a propelling nozzle used in a rocket engine to expand and accelerate combustion products to higher supersonic velocities. Now, at speeds less than Mach 1, thrust is maximized using a convergent nozzle, while at speeds over Mach 1, the optimal angle switches to a divergent nozzle. Don't worry, I'm going to show you a diagram here in a second, but just keep that in mind. So no matter what speed, however, the vehicle seems to be traveling, this B2 angle demonstrates as the optimum angle to maximize thrust. So, we're seeing these geometries having all of these fundamental properties in the universe. So here's a pictorial diagram of what I just told you about. If you look on the left diagram, this is a convergent nozzle. Notice that the wind is flowing from left to right. A convergent nozzle gets smaller as you progress down the nozzle, whereas a divergent nozzle gets bigger. So what we heard, and now I'll show you this equation, when MA, that's the Mach speed, is under 1, then you want a convergent nozzle, but after that, you want a divergent nozzle. I'll go through this quickly. This is called a Condi nozzle, convergent, divergent, and this is the structure that's used in the very fastest engines that we have available today. So they both converge and diverge. But the key point here, no matter which way, convergent or divergent, the B2 geometry is the one that shows up to maximize thrust. So I'm going to show you that through some examples. Prior to the early days of jet engines, they used what were called fixed nozzles. And I'm going to show you those examples because I can't show it to you with a variable nozzle. But in the early days of jet engine, before the variable nozzle came in, that's what we're going to be looking at. And we're going to see this Allison J35. This is a Russian plane with the B2 geometry, General Electric, B2. Here's a Rolls-Royce Olympus engine from Great Britain, B2. But now we're going to go into rocket engines. Now, rocket engines go faster than Mach 1, whereas those commercial airliners were going under Mach 1. So now we're going from convergent to divergent, and they are these diagrams. It's almost like these guys had this knowledge because the angles of these exhaust nozzles are perfect. This is Robert Peltery's rocket nozzle. He was a early 20th century rocket pioneer from France. But here's Werner von Braun's V2 rocket. Perfect. It couldn't be any more accurate than the B2 geometry. So I'm hoping maybe by the end of this that people seriously in the engineering world who probably thought I was nuts before will now start to realize that no, he wasn't nuts. There's probably something to this, and maybe we should explore it. Here's some more examples in contemporary rocketry, the YF-40 from China, the RD-170 from Russia. This is the world's most powerful and heaviest liquid fuel rocket engine. YF-209 from China, CE-20 from India, SRB-A from Japan, the 8K-72K Vostok from Russia, the Rocketdyne J2 from the United States, the SpaceX Raptor, this is what powers Elon Musk's craft from the United States, B2 geometry. And then here's an old Rocketdyne RS-25 rocket. This was what propelled the NASA Space Shuttle. And to end up this section, for those of you who know more about this, this may be of even more interest, but I found this picture when I was doing research, and it's of what's called the NASA EM drive. Now, the EM drive is a concept for a thruster for spacecraft, first written about in 2001. It was purported to generate thrust by reflecting microwaves inside the device in a way that would violate the laws of conservation of momentum and other laws of physics. The concept has at times been referred to as a resonant cavity thruster. B2 geometry. How about that? Our next section is going to take us into ancient architecture. Ancient architecture provides another abundance of GRS angles. The abundance of these angles points to a sophisticated understanding of these and the geometry behind the algorithm. We may find, as we discuss this, that some of you are going to land on one side of that or the other, because I'm actually saying there is a sophisticated understanding of the angles. The question is, did the people know these, or are these relics that were left for us to find in the algorithm? Can't answer that question, but I'm going to show you all of this ancient architecture has these geometric angles. There's ancient nuraghes on the island of Sardinia. There were probably 20,000 of these structures at one point, uh, quite old. They all contain this B2 geometry. The Brochs in Scotland, same thing. These ancient conical structures had these as well. And this is the Great Zimbabwe. This is a ruin in Zimbabwe in Africa. Uh, Michael Tellinger and Dr. Sam Osmanagich measured the level of ionization at this facility, and it was off the charts several years ago. And I'm not at all surprised because it matches the Russian pyramid research with respect to geometry. And here's some melted ruins in Petra, Jordan. Um, uh, B 1.5. I have done documentaries, extensive documentaries on some of this. I'm not going to go into much more detail. However, I do want to bring this up because it's kind of tangential, but I don't think in the end result you'll find it will be. About 2 years ago, I was able to reverse engineer the sacred geometry of all of the Gothic cathedral steeples. And two angles, as you'll see, readily show up here. The Giza geometry, 76.345, and the B2 geometry, which has 27,309. However, the other four angles are different. They're not in the same progression. So what's fascinating is that rather than changing the base width or base length, we take that standard 27,309 geometry with phi cubed as the slant height and B2. We keep the B2 as the base length, but now we change the height of the sides by powers of phi. So what we have here is slant heights that go from phi up to phi to the sixth. So why I'm bringing that up, the 76,345 and the 27,309, both, again, show up in this system, but this is changing the height rather than the length. It almost looks like these angles were set as unique and distinct by the provider of the algorithm to provide either information that we need to dissect. And believe me, when I'm through with this whole series of research, I'm going to come back here and see if these angles interact in any way with the Platonic solids, with theoretical and geometric forms like the amplituhedron and so forth, to see if they relate to higher dimensions. Don't know, but what I'm trying to point out is there's a whole separate system here, and it looks like it's just, at least on the surface, it's nothing more than a different algorithm that's built in to the cathedral steeples. All right, star forts. People have questioned what these are all about and where did they get their geometries and all of that. But they, according to official history, they started popping up in the 15th century. They were built with very specific geometric angles, and the G and SG angles are the most common GRS angles found, although B4 and S4 are also found. So I'm just going to show you a few examples of these. Castillo de San Antón in Spain, we see the G and the SG geometries. This is the Citadel of Alessandria in Italy, G and SG again. Citadel of Saint Martin in France has the Giza geometry. The Citadel of Spandau in Germany has the B4 geometry. Fort Popham in the United States has the G geometry. Fortress Fredrikstad in Norway has the Giza geometry. Leopoldov in Slovakia, G and S4. Manjarabad Fort in India has, and there are many, many more of these that, I could have brought in, but I just want to show you these angles. Now, were these star forts here before? I don't know, but we've got to start thinking that way and asking these questions. Same thing with the onion domes. I didn't know the geometry, couldn't figure out the geometry of the onion domes. They are essentially a Tartarian free energy technology. And these domes their geometry hadn't been figured out before, but sure enough, these angles show up, and we're going to demonstrate that in this section. We're going to start with the Borky Cathedral in Ukraine. We see, I've measured these. These are B2, these domes, and I think there's a B3 or a B4 over on the right. But we've known the geometry of the vertical domes, but these onion domes had not been deciphered by anyone else, and I hadn't done it. So this is kind of new information for everyone. The Ukraine Borky Cathedral onion dome is an SG geometry. And this is a onion dome in Krasno, Belarus. And it is the perfect way to understand and to see these geometric angles that I found from the algorithm. And this is good for two reasons. If you see a picture on the left here, you can see this is a Tartarian free energy or harvesting, ion harvesting technology. We see the fractal antennas up here and the crescent, which are all fractal antenna designs. But what's important here is to look at the onion dome construction and to see these geometric angles inside them. This is great because each piece was milled separately so we could see the specific geometric angles without trying to work through that progression that we see in so many other buildings and angles. The first one, as you see here, is the B2 geometry in the top piece. We drop down to the next section, and it is a B4 geometry. And then if we go down to the bottom piece, we see the Giza geometry. Now, I've taken it further down a few levels, but it gets a little more subtle, so I'm not trying to, overstate the case here, but these three angles are very, very clearly demonstrated inside this onion dome. Cathedral of Our Savior in Russia, Giza. Church of the Resurrection, Kadashi, Russia, Giza. Orthodox Church in Minsk, Giza. Panteleimon Sky Monastery, SG. St. Mary Magdalene Church in Jerusalem, G. Now we'll look at some ancient domes. The domes are architectural elements similar to, the upper half of a sphere, and these domes, again, most of them no one had really figured out their geometry before, but we'll find the Giza, the SG, and the S4 geometries in these domes. Alaska Mosque in Jerusalem, SG. Royal Albert Hall in London, SG. Hagia Sophia in Istanbul, G. MIT, this famous building, at least in the US, MIT Building 10, S4. The Pantheon in Athens, SG. Taj Mahal in India, SG. And the US Capitol Building, SG. I also want to take you on a quick general tour of architecture throughout the world to show you how this shows up in ancient architecture from around the world. First one will just show some brief examples of Hindu temples. There are two basic Hindu temple styles. This is the Meenakshi Hindu temple in India, and this is an example of the Dravidian or Southern Indian architectural style, B2 geometry. This is the Pandharpur Hindu temple. This is in India. Again, the B2 style, but this is the Nagara or Northern India style. You may remember I mentioned the Nagara earlier in the presentation. This is another section further north in India. But again, the B2 geometry, the Nagara style is also well known for demonstration of fractals. This is a Buddhist temple in India, the Mahabodhi Buddhist temple. You've heard of the Bodhi tree and so forth. Well, that's where this is coming from. B2 in the main body of the temple, and once again, B2 in the coil that we see at the top. Very likely this was a free energy technology as well as the Tartarian buildings. This is a Buddhist stupa with B2 and B4 geometric angles. Again, I've got to believe that this, with the coil on top, that this was some type of free energy technology using the principles that we've seen in aerodynamics and fluid dynamics and elsewhere. This is a vihara in Sri Lanka with the S8 geometries, shaped like a bell. Moving into more contemporary architecture, we'll just show brief examples. Synagogues demonstrate these geometric angles. This is B2. Again, B2 for Samarra in Iraq. And here are some from Gothic cathedrals. This is the Leon Cathedral in Spain with the B2. And the Ulm Cathedral, the largest and tallest, excuse me, cathedral in the world, has the B2 geometry as well. Now we'll look at some castles. We see these B2s, and as I say, we'll talk about that in subsequent documentaries. But this castle, all of the major castles have B2 geometries, B1 geometries. Here's Corvin Castle, famous castle in Romania with the B2. But here's an example which I wanted to point out. This is the Drakensberg Castle in Germany. Now it shows B1, B2, B3, and B4. And you see those marked here. There are a couple of duplicate angles, the B2. If you look at these very thin ones, I probably could have gotten a B.5 and or B.25 out of these to finish off the scale. But the interesting thing is this castle was only built in the 1890s. So this knowledge was around only 135 years ago. So I have to question where has it been since then? Hohenzollern Castle, Germany, B1.5 and B2.5. Inverary Castle, B2. Neuschwanstein Castle, B2 and Giza. Now, here's some other major architectural finds. Again, we're finding this progression concept. If we look at Big Ben, we can visualize a B3 progressing to a B2 and then to a B1. Clearly a free energy device with all this free energy, antiquitech up on top. The Eiffel Tower, again, built in the 19th century, but we're going to see this progression. B4 at the bottom, B2 in the next section here between the next section. Then the third section is B1, and that's the section that essentially has this triangular shape in the middle, and then we go up to the top and we see B.5. So get the feeling that these guys knew about this. Now for what many of you have probably been waiting for. As you know, I began and still work heavily with pyramids and make these, but I had never been able to figure out the geometry of all the pyramids around the world. The 27.309 was not found in the apex of any other pyramid. And most of the other pyramid and the Giza geometry didn't show up much either. So the vast majority of the pyramid sites that I knew existed, I couldn't correlate with anything from a sacred geometry standpoint until I looked at nature and came up with the algorithm, found the supplements, and then everything fell into place. So what I'm going to show you here, much more research to do, but when I apply the algorithm to all the major pyramids sites around the world, they all fall within the algorithm. So we're going to see a greater distribution. We're going to have to dig down into the 0.5s and we'll see a B6.25, which again tells me this is a simulation, because drilling down there is probably just to get roughly a 95-degree angle for visualization purposes. But you'll see S1, B3, 3.5, 4, S4, B4.5, S4.5, 5, 5.5 base, Giza, SG, B6.25, and B7. So here we go. This is Altunha in Belize. That appears to be the S4 geometry. Bican in Mexico has the Giza geometry, one of the very, very few that you're going to see with that in the apex angle other than the Great Pyramid of Giza. The Bent Pyramid of Egypt, B7. The Bosnian Pyramid of the Sun, this is where I first noticed this, and it is the SG geometry. Caracal in Belize, SG. You see how these SGs are important? Um, Chachobin in Mexico, another Giza geometry in Mexico. Chichen Itza, B6.25. Comalcalco in Mexico, SG. See how many SGs there are? Uh, Jaccari in Egypt, S4. Dozer in Egypt, SG. El Castillo in Mexico, SG. El Cerrito, SG. El Tajín, SG. The Great Pyramid of Giza, of course, the Giza geometry. Here's an overhead that I decided to try with the Giza complex and see if I could get an angle on the relative positions in the sky, from the sky, of these. And sure enough, the S1 geometry seems to match that that depiction. This is a circular Guachimontones in Mexico, S4.5. Here's a pyramid in Indonesia with the SG geometry. Ichcabal in Mexico with the Giza geometry. Izamal with the SG. You can see how many SGs they are and how important this was to figure this out. Khafre, B5.5. Kenger, B6.25. Khufu, 6.25. Lamani, SG. High Temple, Giza. Mayapan, B7. Maidum in Egypt, B4. Menkari, S5.5. Moral Reforma, B4. Nefertari in Egypt, S6.25. Niuserre in Egypt, B7. Pepi II in Egypt, S4. Sahur in Egypt, S5.5. Red Pyramid, S4.5. Temple of the Inscriptions in Mexico, SG. Teotihuacan, Mexico, B3. Teotihuacan, Pyramid of the Sun, S4. Teotihuacan, Pyramid of the Moon, B5.5. Tikal, B4. Uxmal, G. And Zunantunich, Belize. And all of these angles this is the first time that, to my knowledge, anyone has been able to relate all of these pyramid geometries into one kind of consistent package. And much more research needs to be done here. But I think this is significant. And I think we all now have to I've got to bring the question up at the end of this section. If we are living in a simulation, were these artifacts from some alien culture, or are they part of the simulation? Don't have the answer, but I think we all need to start thinking that way. The final section, 2 sections, we start to get into some really interesting, but I'm sure going to be somewhat controversial subjects. Why will they be controversial? Because of 2 factors. One, I think this is just going to be the kind of the ultimate proof that these angles, that our universe is completely, a simulation. And so that's going to be, I think, upsetting for some. But what we're going to be demonstrating here, I have done this separately. I've measured every angle in every constellation there is, all 88. And what I've done here, I've blown these up and shown them so that you can see as closely as I can possibly do these angles. Now, why is that important? Because we're going to start to find we're going to have to drill down further into the diagram. And some people are going to say, oh, well, this isn't accurate enough, or what have you. But I would request everyone to have an open mind and to look at this. The angles are very, very precise. And yes, we're having to drill down, but we're also going to be seeing a lot of the same angles that we saw in nature, fluid dynamics, and the other areas of this documentary. So with that as background, we'll get started. We're gonna do three angles here. I'm moving myself down so you can see these. Um, Aquarius constellation. Now you're going to see lots of different angles here, but here are the angles that are used. S.75, B1, S2, B.225, S.35, S4, S4.5, 5, B5.5, SG, B6, 6.25. These are not challenging uh, angles in the sense that most of them we have seen all before. So we're going to start now, and I'm going to go through each and every angle, and we're going to discuss, this in detail. So the very first angle is a B1. I cannot see how that can be disputed. It's spot on. We're going to now do the next angle is a B2.25. Again, it is spot on the mark. The Aquarius this angle here, this angle is the S2 geometry and seems to be perfect. Now we're going to measure these angles inside this polygon. And to go back and show it, you see there's 1, 2, 3, 4, 5 different angles here. Now, to go through, as we talked about earlier in the presentation, the algorithm that makes these angles can't sum these specific sets of angles together to come up with the 360 in a sphere or the multiple angles, whatever the number of degrees is for a polygon. So what it has to do is it uses the angles that it has in its bag of tricks, and then it has to come up with a funny one, that to fix the rest of the polygon and make it work. So this angle is the mystery angle, as it turns out, because if we look at the other four angles, the Aquarius constellation, S4.5, spot on. S3.25, again, spot on. B5.5 and S4.5. So these are so precise that it's challenging for me to believe that it's not real, because it all seems to work. Here's the B5.5 angle, and this one again, it's pretty close to 80 degrees, 80.96 degrees. Moving on into the other side of the constellation, we see S4.5, B5.5, and now we're into a four-sided, and we'll see three of these work. The well-known by now B6.25, 95 degrees, the S4 geometry, and S4 again, and there we see the SG and the SG again, and the missing angle in this case is in the corner. So three of the angles we can define, the other one we can't. This angle, S.75, S3.5. The next constellation we're going to look at is the Gemini constellation. That's the twins, as you see, and the angles used. S1 once, an unusual one, S1.125. That's about as far down as I've had to dig, but that's used once. The familiar B2 geometry is seen twice, and that's in the legs of the twins. And we have S2.5, B4, S4, S4.5, S6.25 and S6.5. And again, those are angles that seem to represent a close approximation to 5-degree increments. And we'll see that as we go through. But, quite a number of familiar angles along with a few that are new. Notice here, once again, we have one of the angles that's the mystery because it doesn't fit one of our angles. So it's sort of the slop angle that makes everything add up to 360 degrees. Again, another mystery angle. The final constellation we're going to show today is the Orion constellation. And you see the angles that we're going to be seeing. There's a couple that are of interest. The B7 and 3/8. We see that 4 times. So this isn't any sort of a random accident. You know, when you see these unusual angles, we've got the two B.6.5s. Again, another example, relatively unfamiliar, but these angles are used for, for specific purposes. And again, if we're thinking about this in the context of a simulation and thinking about it that way, then these unusual angles are really not going to, upset us too much, particularly when we see the tried and true angles that we've seen before showing up in the constellation. So to conclude this section, I just wanted to make some general statements. If it weren't for, if I were to be basing this theory on the constellations alone, I would not advocate it because objectively speaking, I'd say, the margin of error might be such in the distribution. One might question whether, this is random, but we know that the evidence that we've seen so far is very, very solid. And when we see the predominance of those very angles in these as well, and that all we're really having to do is to drill down, in certain cases, another level, maybe once or twice a second level to get these, and also couple that with some of these unusual angles showing up multiple times. I am comfortable at this point in asserting that this is indeed a genuine phenomenon, and that with further research, I'm sure we can further confirm the results that we've found in the constellations. The final section in the documentary, before we do concluding remarks and next steps, is the street grids. This, like the constellations, I was guided to do this, and so I took this very seriously. Many people have suggested that sacred geometry is found in the street grids. And sure enough, when I went to look at it and did research on it, I found that, in fact, that is the case. Uh, I'll give the same caveats as I gave with the constellations. It's very possible, and at least in the street grids of Paris and DC, not so much with Versailles because they're fixed. But the street grids that we're going to see, I've taken two circles, and it's possible that those angles have changed since those were originally done. But I will tell you that they all match up to one of these primary, geometric angles. So we're going to look at Versailles, which is the first place that I heard. The first place I found these was Washington D.C., but the developer of the street grid in D.C. learned. He was French, and he learned about this from the Paris of Versailles. So we're going to start with Versailles, then go to D.C. and Paris. So within Versailles, here's a map of the Palace of Versailles grounds. All I've done here is to take some of the major angles and demonstrate their use. Here's one of the B5 geometries. Here's another B5 geometry. Here's an SG geometry. These are all along the Grand Concourse here. Here's a B4.5, an S8, a B7, and a B2, and another B2. So now we're going to look at DC, and I've done all the circles in DC, and they all kind of show the same results. But I'm going to focus here on DuPont Circle, and we'll just start at 12 o'clock and move around, and we'll see all of these sacred geometric angles. So the first one here is B 3.75, then B 1.75, B3, B 1.75, B 2.5, B 3.75, B 1.75, and B3. Now, finally, Paris, the Arc de Triomphe, will do the same thing. We're going to start at 12 o'clock with the B2 geometry, see another B2, a B 1.75, a B 2.5, another B 2.5, a B 1.75, B2, B2, B 1.5, and B2. And finally, B4. So we've gone around the clock here, and here I think actually, the precision. I'm even more comfortable with the precisions here in Paris than I am with the ones in DC. And I kind of get the feeling maybe these street grids, because DC was done later, maybe these have been less subject to alteration over time. I don't know, but anyway, all of these street grids deserve, much greater attention. This is really more just anecdotal, further anecdotal information that makes me think that, the simulation hypothesis is true, and that perhaps, this again is part of the culture that has been pre-planted into our simulation. Certainly, I'm looking forward to hearing a lot of discussion about some of this, and getting feedback from others as well. But this concludes the main section of the documentary. I'm going to be back with some concluding remarks in a moment. Well, if you've made it this far, you must be definitely interested in simulation theory, but I thank you for listening and uh, taking the time to pay attention to something that I think is truly important and foundational, which is the discovery of an algorithm that demonstrates that we live in a simulation. So I have taken great lengths to attempt to make this as accurate as possible and as complete a depiction as possible. Uh, I totally want and appreciate any and all feedback because it's going to make this information better. Uh, I'm not doing this for any other reason than to get information that I think is fundamentally sound and important, and any improvements, enhancements, or modifications and refutations of this are open, and I welcome them in all respects. But with that said, I want to talk about next steps because I think the information we provided or here is profound, and it's going to make some major changes in a lot of different areas. So I want to just talk to those briefly. So I'm going to put together a little list and go back to the slides. So I want to talk just briefly about next steps in each of these areas. Uh, I believe that this is foundationally important information that validates with visible signs that simulation theory best answers the data that we presented, namely that a scaling angle has been found, which is used in any number of different places, showing that we could only be living in a simulation, and further proof that the Nobel Prize from 3 years ago it truly did indicate the death of local reality physics. So I'm really interested in getting feedback from some of the real experts in this field. I have been learning a lot over the last 6 months once I discovered what I had found to try to incorporate theories and concepts and to be able to answer questions from those folks that I have seen, but look forward to having a chance to getting their feedback and discussing simulation theory and the implications of this with them. In terms of biological science, I do believe we're on to a fundamental shift in the way and a demonstration that biology and all the physical sciences need to go in a totally new direction. There is no information, to my knowledge, that demonstrates the quantization of the geometry of growth, this fundamental organizing principle of the universe that's been found before. But I'm looking forward to finding academics that are interested in pursuing this. I just can't believe that there's not going to be, once people can accept this is a whole new, this is the beginnings of the decoding of our non-local world and the simulation algorithms that are behind it. So I think this is fundamentally important. If anybody is, I'd love to collaborate, get any group that's interested that would like to take these things to the next step and really start to make a science or subdiscipline within the biological sciences here. Contact me. I'm going to give some information at the end of the documentary. The same thing can be said with fluid dynamics. I know I've tried talking to people about this before, computational fluid dynamics folks and so forth, and it never went anywhere. I'm hoping now that they see that this could actually, it's not pie in the sky, but could actually be it is reflective of the organizing principles of the universe, that maybe we can find some people who would be willing to try this. I would love to find out and get some real testing done with these angles to see how they may enhance or improve all of the plethora of these topics that we've found, whether it's in fluid dynamics or architecture, free energy, telecommunications. All of these areas are going to be impacted by these geometric angles. So anyone with contacts or interest in these areas, give me a call. And again, I'm going to talk about free energy one more time. There are two ways that I think this could potentially be beneficial. One would be, again, with ion harvesting technologies that existed in the past, but also with respect to nuclear fusion. We know how to fuse atoms right now. We just don't know how to make that implosion occur with the minimum amount of energy. We've seen these geometries now in action in numerous contexts, free energy and so forth. So perhaps using these geometries in conjunction with those by those firms, and there are a number of them that are using implosion type geometries, we may just be able to get over the hurdle of getting over unity with fusion research. So those are very, very interesting areas from my perspective. I'm going to be doing a lot more work in the pyramid area with some other researchers in this field, and we're going to, be doing further research in those areas. If there are people who would like to, help with that or have interest in those areas as well, I'd love to talk to you about that. Finally, I want to start to look. I've done this on a very preliminary basis. There appears to be some connections with these geometries in areas like the platonic solids, the amplituhedron, and as I mentioned earlier, the Gothic cathedral steeple uh, paradigms. I want to look at all of those in conjunction with interdimensionality and see if there's stuff to be done. But that's research for down the road. We've got plenty of information here that I want to get disseminated and out into the community. This is exciting new research, and I'm so grateful to the universe for having had a chance to put this together and to provide this to mankind. And I hope that it does a tremendous amount of benefit. I would encourage all of you, this is the kind of research that everyone can do. You can be your own researcher. And that's the beauty of this. You don't have to rely on me to tell you whether what I've said is right. Go out and test it for yourself. So um, if you're interested in doing that kind of research, I would suggest, I don't get any money for this. This is just the best application, protractor app application that I found for this. But get your protractor app at iconico.com. And that's the one that I've used here. And the other thing that I would do is I have a spreadsheet, and I'll be happy to teach anyone who wants to do this, the math and of this special spreadsheet, because it figures pyramid geometries far, far easier than anything that's online. You can put it, you don't have to start with height and base length as you do on all the other online pyramid protractors. I had a PhD student from the University of Missouri make this for me, and now you can use angles and hold other things, many things constant as inputs, and it's just a tremendous way to do it. So if you're interested, give me a call at the contact information here, and also uh, get that information or call me if you're interested and contact me, in doing research in any of these other areas. So um, help us get the word out on this because again, this isn't me. I want humanity to get this and to see it and to realize that, you know, the world we're living in is not what we think it is. So I'm interested. I want feedback, first and foremost, positive or negative, but let me know, and I'll, but help us to get this out. Most importantly, though, in terms of getting the word out, distribute this on social media. If you know people, if you're influencers, whatever, if you are an influencer, help us to get this out on social media. I'm probably going to be putting up a Facebook page on golden ratio scaling. I think I will. That will help to give us a place to coordinate feedback and information in this topic. Help us with that. I want to do interviews with social media influencers and so forth to get this word out. So if any of you, can help with that, I'd love to do interviews. Academic conferences and articles, I'm willing to help with that. I think there are, organizations of experimental biology and all sorts of organizations, experimental fluid dynamics and so forth, computational fluid dynamics that might be interested in this. And if people are interested, I'm more than happy to present presentations and to help people to formulate ways of incorporating this information into their specific fields. And finally, contacts within biological sciences and engineering. Love to get this information, accepted in the academic community. Biological sciences is clearly perhaps the most important first one to do it, but once it gets accepted there, it could also get accepted in the engineering fields as well. So lots of good stuff to do. If you're interested again in contacting me, here's my contact information. Charlie at Stargate Pyramids, my phone number. Here are my two websites, stargatepyramids.com, where I make my pyramids and sell them, and also the Pyramid Science Foundation.org, which is the website for the nonprofit foundation. For those of you who do YouTube and Rumble, all of our documentaries are found there on the Pyramid Science Foundation page. So I thank you all for watching. It's been a long journey, but I hope you've gathered a lot of good information. I have learned so much in putting this together. It has literally changed my life, and I hope that this information will change yours as well. Thank you for watching, and have a wonderful day.